Welcome to the morning OOPSLA session on semantics. My name is Ilya Sergey, and we have 5 exciting talks to hear. So just a reminder to the speakers that to stick with a 15-minute talk. If you're not sure, just look in my direction. I'll show you 2 in 1 minute before the end. And with that, Robert Jank will be the first speaker of the session. He's from UT Austin, and he will talk about pure demand operational semantics and program analysis. The floor is yours.
All right, thank you so much for the introduction. I'm Robert Zhang from UT Austin. I'm a first-year PhD student there. Today, I'll talk to you about pure demand operational semantics with applications to program analysis, which is joint work with Scott Smith at Johns Hopkins, where we did the work. Now, before I get started, I will briefly overview how we typically do operational semantics for functional programs. There are typically 2 approaches to resolving variables. On the one hand, we have the classic lambda calculus, which substitutes variables for values or expressions, depending on the concrete binding strategy. On the other hand, we have these abstract machines that keep track of variable to value mappings by keeping them in environments and then attaching these environments to function values to form closures. Now, very different from both these approaches, our pure demand operational semantics does not involve any environment or substitution. Instead, we maximally compress the machine state by including just 2 things. 1, the thing we're evaluating, whether it's a variable or expression. 2, a call stack, which is just a list of source program points or function applications. It is presented in a big step style, which has some benefits, but is technically not required. A judgment in our system has the call stack sigma to the left of the turnstile, the thing we're evaluating to the right of it, and the resulting value v. Note that there's no environment anywhere in this system. The key idea is that rather than eagerly propagating variable bindings forward, we will look backward along the control flow to recover values for variables. As you will see soon, local variable lookups are pretty straightforward, while non-local ones are challenging and may require re-evaluating certain components. Now, what could this be good for? Well, we argue that since we greatly compress the machine state size, we're able to better support executing programs starting from the middle, because we only need the call stack in addition to the target to jumpstart the execution. This could be good for implementing incremental or resumable interpreters or analyzers, as well as debuggers that can jump to breakpoints. Now, in the second part of this talk, I will go into how we extended our program operational semantics to support a new kind of program analysis that avoids having to finitize domains ahead of time and instead infers recurrences. I would argue that this kind of state compression could be useful for formal reasoning. Now, in the rest of this talk, I will proceed to define our operational semantics and then briefly go over how we prove this correctness. And then we will briefly talk about the pure demand program analysis, followed by evaluation and conclusions. Now, let's first take a look at our grammar. This is essentially an extension to the pure lambda calculus grammar with a few changes. For example, we define call stack sigma to be lists of call sites or function applications. We also attach these call stacks to function values to form closures, where we replace the usual environment mapping. We use the brain indices to indicate lexical depth for variable uses. For example, the variable y here is a local variable and thus has the brain index 0 because it's bound to its immediate parent function. However, the variable x has the brain index 1 and is non-local because it's bound to a function that's 1 layer out. Now, in the paper, we first develop a set of rules for based on the pure lambda calculus, but then soon extended to include basic data like integers and booleans, as well as records, which then allow us to encode variants and lists. Again, we are the big step. We assume a big step style with a judgment in that form. We can either be call by value or call by name. The paper uses call by value, but for simplicity, we will present this talk using call by name. It's important to recognize that the conversation of whether variable lookups are eager or demand is completely orthogonal to whether we do call by value or call by name, because the point of a demand-driven system is to not eagerly propagate variable bindings forward. Now, here are the set of rules for our core theory. We have 4 rules here. 1 rule is to evaluate function values. The other 2 are to look up variables. And we have another one for evaluating function applications. I will now proceed to highlight a few key details. First, when evaluating function values, we will attach the current call stack to it. When evaluating function applications, we will first evaluate the function being applied, E1. And after getting a result back, we will discard the call stack in its closure, and instead push the current call onto the call stack to evaluate the body of the function being applied, which is E. When looking up a non-local variable, we will first pop the top frame from the call stack, and evaluate what's being applied there. So it's E1 in this case. And after getting a result back, we will use the call stack in its closure to carry on the lookup of x by essentially hoisting x one lexical level out, which we also indicate by decrementing the brain index by 1. Eventually, though, x will become a local variable, at which point we will again pop the top frame from the call stack. But this time, we will evaluate the argument E2, whose value will become the result of the lookup. Now, to illustrate, I will briefly walk through a simple example making 2 consecutive function applications. Let's first start from the outermost application A1, which is highlighted. Now, we can apply the application rule to evaluate what's being applied in A1. In this case, it's another application, A0, which is highlighted. Since it's another application, we will again try to evaluate what's being applied in A0. In this case, it's finally a primitive function, which is highlighted. So now we invoke the value rule to return it while attaching the empty call stack to it. At this point, we're ready to continue evaluating the A0 call by pushing A0 onto the call stack and evaluating the body of the function being applied as highlighted. Since it's a primitive function value, we will return it while attaching the current call stack, which contains A0. Now we're ready to continue evaluating the A1 call. We have essentially finished a recursive call, and we're ready to go back. No, I mean recursive evaluation. Now, notice that we discard the call stack in the closure of the function being applied in A1, which is the call stack containing A0, and instead push the current call, which is A1, onto the call stack. We will use that to evaluate the body of the function being applied, which is a non-local variable x. Now, to look up a non-local variable, remember that we want to pop the top frame from the call stack, which is A1, and look at what's being applied there. As highlighted, A0 is what's being applied in A1. Notice that we have already done an evaluation on A0, but we want to repeat it here to get the same result, but this time we will use the call stack here in the closure to carry on the lookup of x. So we will use this A0 call stack to evaluate x with the brain index 0. So since it's a local variable now, we will just, again, pop the top frame off the stack, which is A0, and look at its argument. And the argument is, as highlighted, 0. So 0 will be the result of looking up x. Now, to briefly go over how we proved correctness, we first defined a reference environment-based theory, which is completely standard. We then state and prove that our system is sound and complete with regards to this environment-based theory. To actually do the proof, though, we need 2 intermediate systems that help get us there, closer and closer to the environment-based theory. We then tie the proof end to end and finish it off. Now, let me briefly go over our extension to a program analysis. We inherit the big step style of the underlying operational semantics, which has the benefit of being more accurate due to the implicit call return alignment at each node of the derivation tree. For a program analysis to terminate, we adopt the standard practice to limit the depth of the call stacks to k frames. However, a novel problem for us is that in order to look up variables, we need to know the fullest extent of the call stack. So in order to recover this full view of the call stack, we try to stitch the current call stack with all compatible k-array stack fragments we have seen so far, which we accumulate in a set on the side as we execute. Our program analysis avoids having to come up with abstract domains to finitize domains. For example, we don't need to come up with these negative, 0, positive domains for integers ahead of time. Instead, we're able to infer finitary recurrences from our big step proof trees and then translate them into constraint horn clauses to be solved for various purposes. Now, to illustrate stack stitching, I will go over a simple example, which is a recursive sum function that breaks down a number into ones and then sum them back up. I've labeled the recursive call as A2 and the overall call as A1. We also have a set S of all the scene fragments so far. For simplicity, I limit the depth of these stack fragments to 2, whereas I limit the current call stack to depth of 1. Now, let's consider looking up variable n with A2 on the call stack. Observe that the fact that A2 is on the call stack means that there must have been at least one recursive call to sum before looking up n. Now, one may attempt to just apply the local variable lookup rule to pop A2 from the top of the stack and evaluate its argument, which is n minus 1. Well, the problem here is that we're left with nothing on the stack while having to evaluate stuff, n-1 in this case. So how do we fix that? Well, we adopt a simple approach of trying to match all the scene stack fragments in set S with the current call stack and see which ones match. So for instance, in this case, the two boxed stack fragments are compatible with the current stack because they all have A2 at the front. So we select them and drop A2 from them, and then we're left with these two singleton call stacks. We will then use both call stacks to evaluate the same expression, n-1, and then after getting results from both, we will merge them. Now let's carry out this process. We have two paths to explore, one on the left, the other on the right. The left path is simple because A1 is on the call stack. A1 refers to the overall call, sum of 2. So we're immediately able to look up n from n in this n-1 to be 2 and calculate 2 minus 1 into 1. However, on the right, we have A2 on the call stack. This means that eventually we will reach the same question we have asked before, which is we're going to try to look up n again using the same call stack containing A2. So notice that these are two identical questions. So instead of cycling here on and on, we will be able to terminate, thanks to our state compression, by halting with a stop value. This stop value will be labeled with the current program state, which consists of the variable being looked up as well as the call stack. And now we're able to give a result for the overall lookup of n. This just combines the two results from both paths. On one path we got 1, on the other path we got a stub minus 1. Notice that this overall disjunction is labeled with the same program state as the stub. So with such recurrence results, we're able to translate them into constraint horn clauses to be solved by an off-the-shelf solver like Spacer. This allows us to, one, recover precision at if conditions, because we don't want to always evaluate both branches of conditionals. Well, if Spacer fails to give a definitive answer, we will just fall back to not being precise, where we will just explore both paths. And the other thing is, it allows us to insert custom user-defined assertions along the program. For example, if I want to assert that the overall call sum of 2 gives a non-negative result. Now, I'll briefly talk about how we evaluated our tool. We compared us against two state-of-the-art higher-order program analyses and used the same set of benchmarks to evaluate them. It turns out that we are a bit better in terms of expressive power, as in we infer tighter bounds from expressions without having to let user predetermine those abstract domains. For running times, though, it's interesting to see that we are either much faster or much slower, which may mean that our thing is useful for speeding up program analyzers, but we need to do more work to understand it better. Here's a performance chart to illustrate that. As you can see, it's very fast. Our thing is very fast on standard programming patterns in most of these benchmarks. However, there are a few cases that timed out. That's not shown on the graph here, on the chart here, that involve either non-primitive recursion or exhibit high computational complexity. So examples include the Ackermann and Takeuchi functions. To conclude, we have defined pure demand operational semantics that maximally compresses the program state and is provably equivalent to standard operational semantics. We also extend it by directly finitizing it to become a program analysis that approximates call stacks via stack stitching. It's also able to extract recurrences instead of having to finitize space ahead of time. It exhibits a very different performance profile. Now, if you're curious for more, please feel free to scan these QR codes to access the paper and code, and chat with us and reach us by email. Thank you very much.
Thank you for the very nice talk. I have plenty of time for questions. Who wants to start? OK, I'll start. So I'm not sure this is actually super relevant, but demand analyzer is a big part of GHC, the Haskell compiler. And by demand, the GHC means a blended abstract domain on the absence, whether something is used or not used at all, and strictness. And that allows lots of optimizations like lambda floating, let floating, and whatnot. So granted that, so could you elaborate, is there any relation between your demand semantics and that, or maybe your semantics could be used to prove something like soundness of strictness and absence analyzer?
Well, I gotta say, I don't immediately see a connection. I'm not an expert on the Haskell part of the world, for sure, but I don't think you're talking about like lazy evaluation, but that's a big thing for Haskell. And that is orthogonal to us because, as I said, our thing is not really talking about call by value or call by name. We're talking about not propagating variable bindings forward. But I'll have to look into what you said later to give you a better answer, unless other people have better ideas here. Sorry.
Okay, thank you.
Yep.
Yes, Ben.
Yes, do you have data or benchmarks for the performance?
Yes. This is showing pretty much most of what we currently support. We use our own DSL that supports only a fragment of the whole set of benchmarks, so we're only able to compute these. If you want to take a closer look.
So anything that the benchmarks have in common in the cases that you're much faster or when you're much slower? What have you learned so far?
Yeah, those would, right. Thank you. That's a good question. I think the benchmarks where we perform very well on, those generally don't involve non-primitive recursions, as in they only use the kind of, the simple recursions that at most mutually call each other, reference each other. And they just do normal recursion with conditionals, with pattern matching, stuff like that. For example, we got examples, we got a rather involved example that involves mapping over a tree by passing in a function. So we're able to handle those pretty fast. However, if you look at this loop-to-one example benchmark, this one involves two mutually recursive calls that are nested in a kind of weird way, in a complex way. So we're much slower than the other two here. So one explanation for our performance profile is that even though we also cache the program analysis based on for example, the expression we're evaluating, the call stack, and the set of stack fragments S, there are still far too many states overall for cache hits to be frequent. So we're still trying to understand the profile better.
Other questions? Yes.
So I'm curious just about asymptotic efficiency. So like maybe if you have a recursion or something like mutual recursion, you have to look back up in your stack a lot.
Oh, okay. There's one edge case where our interpreter doesn't fare very well, which is long tail recursive call chains. Like if you have an extremely long chain of recursive tail calls, then it means that we will have a call stack that's really long for the interpreter. And we need to keep that in memory. So that's not very memory efficient in that case, which is not what you're talking about, but that's one case. In terms of asymptotics, I don't think we have a definitive answer for that yet.
Yeah.
It's probably polynomial to like a pretty big. Okay. Yeah.
Yeah.
So
thank you so much. This is a really interesting work. Thank you.
Thank you.
Thanks. Other questions? Okay, if nothing else, I'm going to ask one last question. Any idea how to make that compositional? Because from your benchmarks and your point of comparison, it seems like this is a whole program analysis similar to like what abstract machines do.
That's a good question. Well, since we can theoretically start evaluating in the middle of a program, if we somehow get our hands on the right call stacks for each component, then we can do it. But the question is, how do we get there? I mean, I gave an example of the incremental or resumable interpreters and analyzer. Those are natural examples because when we pause, we can just save up the program state then. But how do we conjure up these different states for different components? That's the question.
Okay, thank you. By the way, if you're interested, why this benchmark is called facehugger and why this one is called MJ01, I can tell you.
Yeah, this is okay. This is drawn from one of your repos, actually. I remember that.
MJ is Midgar Jensen 2009. Anyways, thanks again for the nice talk, and yeah. So, next speaker, please. I think so. Wonderful. All right. Great, let's move on. So the next talk is by Rahul Krishnan from University of Wisconsin-Madison, who will be telling us how to speed up synthesis by using monotonicity. The floor is yours.
Oh, perfect. Okay, thank you. Thank you for the introduction. Hello, everyone. Thanks for coming to my talk. So I'm Rahul. I'm a PhD student at the University of Wisconsin-Madison, and I'd like to tell you about our work on how we can automate the construction of pruning approaches in top-down enumeration based on proving a semantic property of monotonicity. So I'd first like to discuss the pipeline of how domain-specific synthesizers are typically developed. So first, you would define a synthesis problem, which is typically defined as a behavioral specification and a search space. For this work, we're mostly going to focus on when the behavioral specification is a set of input-output examples, and our search space is defined as a regular tree grammar. Then, typically, a domain expert would step in and construct a bunch of manual observations whose insights will then be used to inform a synthesis algorithm that is manually constructed. And so the problem here is that these observations have to be manually constructed, and therefore this algorithm manually developed for each domain. So the goal of our work is to automate this process for a large number of domains. So a very simple but effective strategy for synthesis is that of top-down enumeration. The idea is that you'd start with you would enumerate programs in increasing size of, let's say, of the size of the abstract syntax tree until you find a program that satisfies your behavioral specification. The problem is such an algorithm, when done naively, leads to an exponential blow-up. And so a traditional way to solve this problem is to consider templates like the one we have here, where a template is an abstract syntax tree that contains a hole, that's that square thing, that represents an empty context that can be instantiated with any derivable term from that non-terminal. And so notice that a template represents a set of programs. And the set of programs in this diagram here that is part of that template, I've highlighted in yellow. And so the idea is that if we can somehow prove that this template cannot satisfy our behavioral specification, meaning that no derivable program can satisfy, no derivable program from this template satisfies all of our behavioral constraints, then what we can do is then prune that template, which then lets us prune this entire set of provably incorrect programs. And so notice that this set is potentially infinite. And so what we're able to do is we're able to guide our synthesizer away from provably incorrect programs and towards more likely ones. So top-down enumeration has actually seen success in a lot of domains, such as regular expressions, imperative programs, SQL queries, and data log programs. And the key to scaling all of these approaches, we're coming up with this sort of pruning approaches via coming up with domain-specific observations. So let's actually look at a couple of example domains. On the left, we're going to be considering the pruning approaches for regular expressions. And on the right, we'll be considering the pruning approaches for imperative programs. So a tool like AlphaRegX is a synthesizer for synthesizes regular expressions. And we'll try to we'll consider these templates in order to try to prune these templates away. And the way a tool like AlphaRegX would approach this is by constructing upper and lower bounds on the language of this regular expression. So we can construct a lower bound by replacing that hole with the least permissive regular expression, and construct an upper bound by replacing it with the most permissive regular expression. And then if we know that if any of the behavioral constraints fall outside of these bounds, we can prune this template away. A similar process can be done in the imperative case, where a tool like Simple will construct a range of values for the outputs of the variables in our program. So in this case, just as an example, we'll see that no matter what we instantiate our hole with, x will always be bound. The output of x will always be bounded by 0, since it'll never change, and y is unbounded, so it can be any integer between -infinity and infinity. And if we know that any of our behavioral constraints fall outside of these intervals, then we can prune this candidate away. So what we're going to show, what we showed in our work, is that while these approaches seem different and were the major contributions of these individual papers, we show that these can actually be reasoned about in exactly the same way. And the way we're going to do that is by constructing interval abstractions that over-approximate the set of possible values that these templates can take on. And so notice that the observations these domain-specific tools made actually end up matching the intervals that we generate. And so the main contribution of our work is that we're able to unify these approaches under a single umbrella of interval-based abstractions. So let's actually discuss how we generate these intervals. So let's reconsider the ASTs from before. We're going to start by generating intervals for the leaves and construct abstract transformers to generate intervals for the whole AST. So the 0 is a concrete value, so we know it can be over-approximated by the singleton interval 0, 0. And for now, we're going to replace our whole with the widest possible interval, or top. So in this case, our interval is going to be from the least permissive regular expression to the most permissive regular expression. And then I claim that a sound interval transformer for this concatenation operator is simply just applying the concatenation operator to the left and right bounds of our of its children. And so I've colored the left bounds in purple and the right bounds in blue to show this. And a similar process can actually be done in the imperative case, where again we construct intervals for the leaves, we propagate these intervals up, specifically by constructing these interval transformers by applying the concrete semantics of each of these terms to each of the endpoints. And so these intervals are sound for the examples I've shown, but they may not always be. And so in order to automate this process, we may ask, when is this actually possible? So let's look again at our concatenation operator to gain some intuition. The concatenation has this really nice property that if, let's say you take two regular expressions, R1 and R2, if we know that the language of R1 is a subset of the language of R2, then if we take a third regular expression, R prime, then we know that the language of R1 concatenated with this third R prime is a subset of R2 concatenated with R prime. And this is true even if we swap the order of concatenation. And so this gives us intuition for our notion of monotonicity, which is that we say, suppose we can prove our concrete semantics, F, is monotonic on each argument with respect to some order, where monotonicity in this case is just the standard definition of monotonicity. Then we can get the abstract transformers, this F-sharp thing, simply by applying this endpoint recipe that I talked about, where we take the intervals as inputs and apply our concrete transformer F on the left bounds and the right bounds respectively. So to connect this with our example above, in the case of regular expressions, our order here was just language inclusion. And what's nice is that the abstract transformer that we get here was effectively acquired for free given a proof of monotonicity. So these interval semantics have some nice properties. The first is that they're sound. We showed in our work that these are sound, in the sense that for any template, the interval that we construct will cover the set of possible outputs that any derivable program could output. It's also precise, in the sense that for it's the tightest possible interval that is also sound. And finally, we show that this process can actually be fully automated. So I mentioned in the previous slide that given a proof of monotonicity, we can generate our intervals pretty easily. But we show in our work that we can actually, given the concrete semantics of the terms in our language, we can query an SMT solver for proofs of monotonicity, and therefore fully automating this entire process. And so this is the monotonicity is the sufficient condition to generate these intervals and rationally reconstruct the approaches we saw in domain-specific prior work. So we generated these precise interval transformers for operators that could be proven to be monotonic. But we actually found one other way that we can make our interval abstractions for the whole abstract syntax tree even more precise. And so that comes from the observation, well, this comes from something I said earlier in the talk, which is that currently we set the interval for this whole to be the largest possible interval top. We just sort of defaulted to that. But there's this question of what if we can learn more things from the grammar? So As a very simple and restricted case, consider this non-terminal where we take E and it just goes to the number 0, 1, or it can recursively add 2 terms together. Like I said before, we currently default this interval, the interval for this whole to be the interval minus infinity to infinity. But if we look at the structure of the grammar and the semantics of addition, a sound interval that would work is simply just the interval that covers all non-negative integers, 0 to infinity. So what we can do is we can actually replace our old interval of top with this new one, and then propagate this interval upwards until we reach an interval for the entire abstract syntax tree that is now even more precise than the one we generated before. And so the way that we would generate this interval is we use a technique called grammar flow analysis. It's an iterative approach where we can start with our interval top and iteratively query for tighter and tighter bounds until we reach an interval that is precise for that non-terminal. So I don't, unfortunately, have time to go into the details of how our grammar flow analysis technique actually works in detail, but please check out the paper if you're interested in more details. But we show that this process can also be automated by an SMT solver. So in this way, we're able to fully automate the construction of these intervals for these holes, as well as these abstract transformers for all of the recursive terms. So both the monotonicity checks and our grammar flow analysis required reasoning directly about the semantics in order to generate these interval over approximations. And really, the ability to directly reason over the semantics is what the SEMGIS framework gives us and is what actually enables our entire technique. So for background, the semantics guided synthesis, or the SEMGIS framework, is a domain-agnostic framework that allows a user to supply their own semantics to the terms of the language. So before I said this synthesis was defined, the synthesis problem was defined over a search space and a behavioral constraint. But now there's this third element of the semantics that can be given as input to the synthesizer. And this user-defined semantics is actually what is unique to the SEMGIS framework. So now, given the semantics, we can actually then apply the techniques that I've talked about in this talk to then encode whether a semantics is monotonic and perform grammar flow analysis. The whole process which can be automated using an SMT solver. So for our evaluation, we tested our framework by building a synthesizer that takes in benchmarks from the SEMGIS framework and generates the abstract intervals that I've described in this talk. And so we evaluated on a number of benchmarks from a number of domains, and we wanted to, compare the performance of our tool. And so in this first graph, we wanted to evaluate the performance. So in this case, the way you would read this is down and to the right is better, as that indicates that tool is faster on more benchmarks. And what we see is that the brown line, which I guess is very close to the black line, which is so the brown line is our tool that generates that performs pruning, that uses the intervals from both the monotonicity proofs and the grammar flow analysis. That outperforms both the baseline, which is just a naive enumeration that doesn't have any pruning. That's the blue line, as well as our ablation, where we only generate intervals using just the monotonicity proofs, but not our grammar flow analysis technique. We also wanted to see how effective it was at searching farther in the search space. So this graph is on benchmarks that the tools were not able to solve. And so in this case, actually up and to the left is better, as that indicates that that tool was able to search much farther in the search space. And what we see is, again, that brown line outperforms both our ablation and the baseline naive enumeration. Okay, so in conclusion, we started with this pipeline for the domain-specific solvers, and we replaced the domain expert with this new pipeline that is able to automate the process for a large number of domains. And so to recap, we start with the synthesis problem that is defined in the SEMGIS framework. I unfortunately didn't have time to talk about this in my talk, but for the definition of monotonicity work, it inherently requires an order. We have a way to find a good order to use for these monotonicity proofs. We then run an analysis that involves generating monotonicity proofs and grammar flow analysis based on the semantics, and we show how this can be fully automated by an SMT solver. And this analysis can then be used to generate interval semantics that we've seen can rationally reconstruct prior interval approaches in domain-specific tools. We can then feed these intervals to an enumerative solver that allows one to then prune partial programs, which we have shown in our evaluation allows us to synthesize solutions faster as a result of these pruning approaches. So we think this opens the door to a lot of future work. The first is that the order that you use to generate your intervals can actually lead to different types of intervals being generated. So how do we sort of leverage different orders and different intervals for better pruning? We focused entirely just on the interval abstract domain, but are there other abstract domains that we can automatically come up with by analyzing the semantics and that we can use for pruning? And finally, we focused entirely on top-down enumeration. But is it possible to perform this kind of reasoning on other type of synthesis algorithms as well? So SemGIS solvers are still in their infancy. So we hope that ours can be the first in a series of improved solvers that are able to leverage analyzing the semantics in order to improve the performance of synthesizers. And so with that, I'd like to say thanks again for coming to my talk.
Thanks for the very nice talk. We have time for questions. First you, then others.
Hello, very nice talk. So I'd like 2 questions. So first one is that when you say you have to apply the abstract transformers, you have to define the abstract transformers for each operation in your grammar?
So the abstract transformer that's the interval construction I was talking about from the monotonicity proofs.
For addition, you have to do add. For subtraction, you have to minus. So for each operation in grammar, you have to give abstract transformer differently, or you generate automatically?
We generate it for each term in the grammar.
Okay,
Yeah.
sure. So the second question is like when you said that you have compared with your baseline for the same gas.
Yes.
So have you tried with your optimization for the same domain? Like if you have you tried with your timing with SEMGAS and the sketch for the for same kind of domain? Have you tried different solvers, synthesize engine with your tool? Because you compared with your baseline SEMGAS, but
Yes.
for different domains there are different synthesis engines.
Right, right.
So have you done this comparison, like what sketch that's in how or CBC5?
So
what
we
you-
did not. So the reason is that the SEMGIS framework is much more general than these.
And
Yeah,
I agree.
but
I agree.
like-
I'm not comparing for different domain.
Okay.
Fix the domain. For that particular domain, what's your comment on? Will it be better or worse?
You're saying, sorry, just to clarify your question, are you asking whether, how we would compare our solver
means,
against something like Sketch, which,
Yes.
okay,
Yeah.
so we did not perform that comparison,
Because
but our set of benchmarks, if we tried to compare against Sketch, there are a lot of benchmarks in our problem set that Sketch would not be able to solve, just because of the generality of the SEMGIS framework. And so we weren't able to perform a direct comparison that way. Oh, sure, yeah.
All right.
Hey, I was just curious. So this looks very similar to Morpheus to me, in that it seems like it's essentially a very similar algorithm, but just customized to the interval domain. I'm just curious if I'm missing something, or maybe could you I guess compare and contrast to that work if you know it?
So I'm unfortunately not familiar with Morpheus. Yeah, maybe Loris can talk about it.
So I think the short answer, I think in Morpheus, you have picked a domain for which you figure out how to do synthesis of transformers. This is the dual of it. We picked a domain for which you do not have to synthesize transformers. Transformers are for free. What you have to figure out is when the transformers can be synthesized for free. And so the idea is that, there is actually this paper we found out about a week ago at POPL this year, where they started to do the similar observation for abstract interpretation in general, that basically monotonicity is what tells you intervals are great. And so there they use it for verification. Here we use it for synthesis, as in, if you're monotonic, then you get these transformers for free. And so that's the big observation of the paper. Versus in Morpheus, it was like, here is one domain that works well. Here is how we synthesize for it. And so it's kind of related but different, yeah.
All right, let's take the rest offline, and let's thank the speaker again.
Thank you.
All right, so full screen. Good. So next talk is by Didrik Lundberg from KTH, Stockholm, and it's on the mechanized semantics for data plane programming. On to you.
Yeah. Thanks for the introduction. Nothing to add there. So first, let's set the stage with an introduction of the setting. Software-defined networking splits the functionality of a network element, such as a firewall or a switch, into a programmable data plane and a control plane. And the data plane implements the forwarding of packets, parsing the headers of incoming packets, and using this to read entries from tables set by the control plane, which specifies certain actions to take, for example, setting next hop IP address. And the control plane is responsible for setting the content of these tables using these data plane logs as well as input from some admin or manager. Programming this data plane then is an ideal job for a domain-specific language. And this language is P4, which is the de facto standard language for programmable data planes. P4 compiles to a very wide range of different targets, like terabit bandwidth switches, such as the Intel Tofino, network interface controller cards, and even the Linux kernel. The hardware running P4 can be very specialized and heterogeneous and may use both ASICs and FPGA components. Performance is absolutely essential here. It's important to squeeze every bit of bandwidth from the hardware, which is reflected by the P4 language design. And when this hardware is increasingly put in places of critical importance, the need to model and verify the P4 language also increases. So what is this language P4 then? P4 programs consist of pipelines of programmable blocks. Parser blocks, which parse headers and work sort of like a finite state machine, and loop-free control blocks, which match against tables in the control plane. And P4 has no for loops or while loops, and the transitions in parser blocks may introduce loops, of course, but such loops are, in practice, always well-behaved and bounded by finite header sizes. And function recursion is also not allowed. There are no pointers and no dynamic memory allocation, and as such, no heap. The language allows specifying and reading from tables which map sets of values, like for example ranges, to function calls. And the entries of these tables may or may not be hard-coded by the P4 program. Extern functions and objects are central to the language, and they provide an interface to specialized hardware functionality, and their implementation is not written in P4. So both tables and externs may hold state between the processing of different packets and may be shared between parallel pipelines, the implication being here that they're interesting to consider for concurrency effects such as interference. Also, functions use a special calling convention where every parameter has a direction. So final values of out-directed parameters are copied out of, from the callee to the caller. And this enables something similar to call by reference in the absence of pointers and allows to control the side effects of functions such as these black box externs. And the characteristics of P4 in this list should then, of course, be used to inform semantics design. Let's look briefly at some example code. So the parser block shown here contains two states, start and parse IPv4. Every state ends with a transition to other states, and the start state selects the next state parse IPv4 or eject by matching the ether type field of the p.ethernet struct. Okay, so the body of a control block as shown here is the apply block as, at the bottom, and in this case the only table involved is IPv4 match, which is specified right above. So Hol4 P4 is our model of this P4 language, And it is at its core a small step or structural operational semantics written in a heapless style, where every function has its own frame, each containing a store with values of all local variables and so on. And these frames are stored in a stack structure and only interact at the time of function call or return. We have also formalized the type system, whose notion of well-typedness guarantees progress and type preservation. And we've modeled some architectures, in particular the V1 model and eBPF architectures, with others like PSA and XSA under development, and the Intel Tofino model that we have not public yet. So our semantics model the entire pipeline from the input to the output of a packet. And all these things are formalized in Hall 4. This doesn't mean that the work is all theoretical, of course, since we've also constructed an import tool to import real P4 programs into Hall 4. So to be clear, what we mean with heapless style is that all variable names map directly to their values. In heap-based models, there's an intermediate layer of memory locations. But since P4 lacks pointers, this additional layer is largely unnecessary. And this heap can, of course, be cumbersome, since you can't just disregard an unused part of it without a formal justification, and it might also need to be garbage collected. Now, aliasing is also possible in theory in heap-based memory, which can be a source of complications. So we use frames to ensure that the view of variables is always minimal. Let's go into more detail about the semantics. Semantics is split into 4 layers, with the architecture layer on top, each defined only in terms of the layer below. The concurrency layer is a bit special, and I'll mention it separately later. So the reduction signature then of the architecture layer, the state, contains list of incoming and outgoing packets, IO bar. The architectural state alpha, which holds extern data and variables passed between blocks. The block index I, which tells us which block we're currently reducing. Global variable maps in gamma G bar, and the stack of frames phi bar and the status T. So each frame then holds the body and local variables of a function that's currently being reduced. Calling a function, of course, pushes a frame onto this stack and returning pops one. And big E to the left there is the static environment containing all the immutable information about the P4 program and architecture. So from this big E, the frame layer semantics keeps big T with information about tables, and big F with function signatures and bodies. And the main role of this frame layer is to use the statement semantics to reduce the top frame and handle copy out between frames. And in doing so, alpha may be modified, since the external objects can be updated, of course, block variables can be set, and status can be changed. So the statement layer semantics reduction has a similar signature to that of the frame layer, the difference being that there's only one single frame being reduced here. However, this reduction may result in a new frame, which we signify here by adding it above the reduction arrow, and this should make it maybe intuitively clear how this heapless formulation restricts the visible variables by construction. So finally, the expression layer semantics also needs the function signatures in big F, as well as the variable maps gamma bar constructed from the frame we're currently reducing and gamma G bar. And note that expressions treat the variable maps as part of the static environment because they can't affect directly the values. And the phi here above the reduction arrow is the new frame that may result from a function call. Architecture layer semantics looks at the whole pipeline from a top level perspective, having only 7 rules for input and output of packets into and out of the hardware, initialization, regular execution, and finishing a programmable block. When block parameters are copied from alpha and back to alpha when initializing and finishing respectively. Transitions between parser states also handled by the architecture layer semantics and signaled by a special status. Finally, it governs functionality that the hardware may perform between the programmable blocks, called fixed function blocks. So the rule from the architecture layer semantics that handles regular execution inside a programmable block does so by using the frame layer semantics. And the frame layer semantics only has 2 rules. Both take the top element of the frame stack, takes the appropriate information from the static environment big E, based on the function name associated with the frame, and then uses the statement level layer semantics to reduce the frame. So in the regular case, the status from the statement reduction does not signal return, and the top frame is updated using the statement semantics with a potential addition of a new frame if a function was called. But if the status was set to return, then the frame return rule can be used. And this rule is responsible for performing the copy out behavior defined by P4's calling conventions. Note that copy out cannot be done at the statement level, since the statement level semantics is unaware of the blocks below in the stack. Statement level semantics has rules for many standard language constructs, such as if statement, return, and so on. So the transition statement is like a go-to for parser state, sort of, that you saw earlier. And extern and apply rules are also P4 specific. Let's take a look. In Hall 4 P4, calling an extern function or extern object method results in a new frame with a body that consists only of a single extern statement, here typeset with a black box viewed from the side. The reduction of the extern statement is performed by first looking up the extern implementation ext in big F. And ext is then a function that updates the architectural state alpha and the local variable map according to the extern implementation. Can also read the global variables, and it can set the status t directly, which is used for return values. But note that this rule uses the heapless formulation to disallow extern functions to directly set variables in other frames, for example, which the semantics must ensure to follow the P4 language specification. For a heap-based semantics, on the other hand, one would have to be careful not to let this ext write to or even read from the entire heap, as this would make it too powerful. And note that this ext can be very complex. So the whole for external implementation in the worst case may consist of hundreds of lines of code. Let's also take a look at table application. And this reduction simply takes the fully reduced key of the table, v1 to vn, and uses the static information stored in big T to obtain a function name f prime and some fully reduced arguments. And the reduction is then to a function call to this function f prime. The expression layer semantic similarly has many standard rules, arithmetic, logical operations, lots of bit fiddling. The select expression used to select next parser state that you saw. But the rule that's interesting here for semantics is the function call. So first, this rule uses the body and signature of the called function stored in the static environment. And then all arguments must be reduced according to direction. So in and non-directed arguments should be fully reduced to values, while out and in-out directed arguments should only be reduced to L values, like, for example, variables. And the new scope, gamma, is then constructed. So in-out directed parameters assume the value of the argument in the caller scope stack tupled with the argument as an L value. And out-directed parameters are initialized with indeterminate bits according to their type, also tupled with the argument as an L value. And recall, these L value arguments are stored so that we know what to copy out from the function, from the frame later when we're returning. And finally, the in and non-directed arguments are just copied in as is, tupled with bottom. The result of the reduction is the function value placeholder star f and the new frame consisting of the function name f, body s, and scope gamma. Okay, so we have also built a type system for our semantics, which is used to prove two nice properties of the semantics in Hall 4. Type preservation simply states that if the initial state st is well typed, and if st is reduced to st prime in the environment E, then st prime is also well typed. The progress property states that if the initial value is well typed, then either there exists an st prime, such as st goes to st prime, or st is a final state. Then we did some other useful things. Now, having defined a set of semantic rules in an interactive theorem prover does not mean you automatically have a way of executing a program. Our semantic rules are relations between states that allow you to conclude whether the reduction from one to the other is valid. You can, of course, define a function that, given an initial state sigma, computes the state sigma prime resulting from one reduction. Effectively, this means just finding which rule to apply and computing the premises to obtain this sigma prime. And this we call an executable semantics, in the sense that you can directly use the standard evaluation mechanisms of the ITP to obtain this right-hand side given the left-hand side. And the semantics is deterministic, so this function only returns a single state to preempt questions. And our executable semantics has been proved sound, and the soundness proof states that every step of this executable semantics respects the relational semantics. executable semantics passes all test cases that can be imported to Hall4 P4 using the import tool when applied to a standard test suite of P4 programs with specifications for complete tests, a process which is totally automatic. To take a real P4 program and put this in Hall4 P4, we've constructed an import tool. Use an external tool, Petra, to type check a P4 program and parse it into JSON, which is then parsed into Hall4 by our Hall4 JSON parser and finally transformed to the Hall4 P4 format by this last stage, which does quite a bit of inlining and desugaring to properly represent programs. And as a proof of concept, we use the executable semantics to prove that the VSS example from the P4 language specification correctly decreases the time to live field of a packet by exploiting the capability of the ITP to evaluate the executable semantics with symbolic initial values and rewriting with assumptions. Was used in a paper to argue that it wasn't hard to construct a sort of complete symbolic executor for Hall4 P4, something we made good on and proved to be true in a follow-up work which was actually presented last week. And this has already been successfully used to verify real P4 programs in industry, largest being somewhere just below 10,000 lines of code. So to show the usefulness of the small step approach, we have also extended semantics with a concurrency layer, and using this we've shown that our model can accurately model interference between parallel pipelines with shared externs using an example from the concurrency model section of the P4 language specification. For future work, something like this could be used to model both the control plane and the data plane. So let's sum up this work, very briefly mention some other effort. Heapless semantics of P4 implemented in Hall4. With the type system with proof of progress and type preservation, the import tool can be used for real programs, and executable semantics that has been used for validation, and all the code is open source and can be found in the Hall4 P4 repo, also with an OOPSLA artifact available. Maybe to preempt some questions again, I would like to compare this very briefly to some other similar work recently published by others, but please check the paper for a more complete review. So several people have formalized P4 in the ITP COC. First, the COC formalization of the Petra semantics, originally written in OCaml for a POPL paper a few years ago. It's no separate publication for this COC version as far as I'm aware. And P4 Cub is an intermediate representation for making analysis tools made by a group at Cornell, including both a big step and a small step semantics. And there's also a group at Princeton that published their work at ITP last year, only working with control blocks in their publication at least, although I suspect there's more unpublished. So all of them in COC. I don't think they're proved sound with respect to one another. There's solid validation done for Petra at least. Main difference being the heapless approach that we use, and of course that we're focused on the small step semantics. Thank you. Any questions?
All right, thanks for the talk. Given that many questions have been preempted, we have time for maybe one or two.
Thank you, good talk. I wonder if termination.
Okay, I'm going to guess
Is termination is a problem for P4 programs?
So, right, so the parser, one could imagine in theory, an evil parser that maybe wouldn't even be possible to compile to real hardware. That would be really nasty to deal with. But for realistic programs, usually this is not that difficult. And with a small step approach, additionally, it's not so difficult to deal with.
So
So I think one of the vaguest things that I encountered in the specification was how, so I mentioned this out directed, exactly. So when this is initially, right, you have these uninitialized values and how to treat them. And actually for this work, they're just sort of a bit improperly modeled as a special type of, but really what I think is the proper way of doing this is that you have sort of a pseudo-random oracle just assigned. So uninterpreted function in the model that then for concrete execution can be specialized to a specific pseudo-random function, but then, yeah, maybe I'm talking too much here.
All right, so let's send Didrik again. All right, and next we have Jixiao Guan from Peking University, who will be talking about semantic lifting for syntactic sugar. On to you.
Thanks for introduction. Hello everyone, I'm Jixiao from Peking University. Today I will present our work, semantic lifting for syntactic sugar. Syntactic sugar is a widely used tool in language engineering. It offers convenient syntax and high-level abstractions, which is suitable for DSL implementation. Such a DSL can be defined as a collection of syntactic sugars built on top of a general purpose language as a host language. For example, E1 and E2 can be defined as if E1 then E2 else false. Here we use arrow D to represent the desugaring rule. However, sugar-defined DSLs face a problem. Consider a user who is an expert in the target domain but unfamiliar with the host language. After writing a DSL program, the code is first desugared into the host language before dynamic execution or static analysis. If an error occurs, the error messages will be framed in terms of the host language. For the user, to understand these messages, he has to learn knowledge about the host language, which can feel like falling into a black hole. This issue is known as abstraction leakage. To solve this problem, previous work proposed the idea of language lifting, which means that given the syntactic sugars to define the DSL and the complete definition of the host language is semantics, typing rules, and other things, we aim to lift the DSL definition according to the syntactic sugars and the host definition. We expect the DSL definition obtained preserve the abstract boundary, which means that for any DSL program, its execution or analysis doesn't touch the host language anymore, and everything is understandable to the DSL users. The typing rules for the DSL have been successfully lifted by previous work, and the abstraction property has been proved. We can find in the lifted typing rule of AND, host language construct if is not mentioned anymore. Naturally, this raises a question. Can we use a similar method to lift semantics? And can we ensure abstraction in doing so? In the case of AND, it's OK. And we'll soon demonstrate how the derivation works. However, after further exploration, we found that directly applying the type lifting method to semantics lifting can easily result in the abstraction leakage. Informally, this is because the semantics definition often involves some non-local and non-compositional evaluations. Such complexity makes the abstraction preservation in semantics lifting more challenging than that in lifting typing rules. And we will explain this later. So our work proposed a set of reasonable conditions, imposing certain restrictions on the syntactic sugars and the host language, ensuring that within this framework, the semantics lifting preserves the abstraction. So next, I will first walk through the algorithm using the AND example. And then, based on this algorithm, I will explain the challenges of preserving abstraction in semantics and the tools we will use to address them. After that, I will introduce the conditions we propose. And finally, I will introduce the implementation and evaluation of our system. So first, the algorithm. Note that the algorithm we use is very similar to the type lifting, and it's not our main contribution. The algorithm takes two inputs, the host semantics and the syntactic sugar. We use big step operational semantics in our framework, and the output is the DSL semantics. For the AND sugar, first, E1 and E2 should be evaluated to a value V if the if expression is evaluated to V. And because we know the rules of if according to the host definition, we can apply these rules and expand the premises. There are two possible cases. And in the red tree, false is a value, so we can expand the premise further. Then, by removing the intermediate derivation and simplifying the result, we can obtain the following evaluation rules of and hide the host language construct if. That's how lifting algorithm works. Briefly speaking, if we want to derive the evaluation rule of the sugar C, we just need to find a derivation of its random handset expression in the host language. Here, an important observation is, if all the evaluation rules in the host language are structural recursion, which means that the result is always premised on the values of its sub-expressions, then after we define syntactic sugar, the intermediate host construct in right-hand side will be stripped away step by step. And finally, the premises will only contain the evaluation of these variables, thereby preserving the abstraction. This property is generally satisfied for typing rules, but not for semantics. So the next step is to break down the non-structural parts of semantics, and we will introduce some gadgets to describe to capture them, and our conditions will be defined on these things later. The first is non-locality, which can be seen in the rule of lambda abstraction. It keeps an unevaluated expression in the result. As a consequence, when lambda abstraction is used to define a syntactic sugar, the body cannot be derived statically and locally because it itself is a value. And if we derive the evaluation rules for and f like before, we will get this. And here, if appears and the abstraction leaks. Such non-local evaluation may cause the abstraction leakage. And to describe such non-local evaluation, we call this E, this body, the non-abstract component of the lambda abstraction. And we design analysis to find these non-abstract components automatically according to the host language evaluation rules. If a host construct is used in this position in sugar definition, like and f, we will reject such syntactic sugar. Actually, it's one of our conditions. The other one is non-compositionality, which can be found in the application rule. There is a premise which is not a simple evaluation of its sub-expressions, and it contains substitution. To isolate these non-compositional parts from generic evaluation, we introduce the concept of meta-functions. Meta-functions can also be used to express primitive computations and operations on set effects. And then, we reorganize the rules of the host language in terms of evaluation and these meta-functions. We will propose the conditions of meta-functions that say, if these meta-functions have certain properties, the overall abstraction property can be guaranteed. Now we can introduce our conditions. Of course, since we have introduced meta-function as a form of judgment, we have to make slight modifications on the semantics lifting algorithm a bit. Due to the time limitation, I won't go into further detail on that here. We have proven that, informally speaking, correctness and abstraction can be guaranteed under the conditions we provide. Here, correctness means that if E is evaluated to V in the lifted semantics of DSL, then DE will be evaluated to DV in the host language. Here we use big D to represent desugaring. And the abstraction means that for any DSL program, the derivation tree of its evaluation doesn't mention any host language construct. And additionally, we introduce a set S to describe the value constructs that are permitted to appear in the DSL. There are 4 conditions. The first 2 are about meta-functions. Meta-functions doesn't generate host construct out of thin air. and meta functions and desugaring are commutable. The third one is about the host language semantics. We require that rules of the host language use no other host language construct in the premises. And the fourth one, as we stated, is about the syntactic sugars. Syntactic sugars uses no host language constructs in non-abstract components. Among them, there are three conditions are about the abstraction, and one is about the correctness. And the important point is that only the condition related to the non-abstract component, the fourth condition, concerns the DSL designer. The remaining conditions are about the host language and the meta functions, which are predefined. And that's not something the DSL designer needs to worry about. There are many interesting implications from these four conditions. For example, hygienic problem, which is a famous problem in microsystem, is related to the second condition. And if loops and recursion are used in the desugaring rules, these two conditions can guarantee that the termination of the semantics lifting. And I cannot cover all of them now, and more discussion can be found in our paper. So now it's time for evaluation. We have implemented our DSL development system in Haskell named OOPSLA. And we provide two basic host language, Lambda Calculus and MiniML. And we implement some extensions based on them by introducing some new data types and effects like references, I/O, and exceptions. And OOPSLA provides an interface to define DSL using syntactic sugars, and the semantics will be lifted automatically. After that, OOPSLA will generate an interpreter and IEPL for the language for free. To evaluate our system, we focus on whether OOPSLA is expressive enough to develop DSL, and whether the lifted semantics protects the abstraction boundary. To answer the first question, we collect 7 benchmark DSLs from the samples of MPS, and we produce them in OOPSLA. And we implement 5 more real-world DSLs. To answer the second question, we show the number of the syntactic sugars to implement these DSLs, and we check the lifted semantics manually. To sum up, in this paper, we propose a framework for lifting semantics for syntactic sugars, and we present a set of reasonable conditions to ensure that semantics lifting will guarantee the correctness and abstraction properties. These conditions are imposed on meta functions, host language definitions, and syntactic sugar definitions. For this idea, we implement the tool OOPSLA, which is shown to be flexible and practical for developing DSLs. And if you have any ideas about the language lifting, I would love to discuss with you. And we also will show our work in the poster session. That's all. Thanks for listening.
Thank you for the very nice talk. Have lots of time for questions. Yes, please.
Yeah. When do these correctness and abstraction properties fail on some? I understand you had all those examples that worked, right? But I don't quite understand the boundaries of like what DSLs would fail these conditions. So when would we be in trouble with your framework with a certain DSL? That makes sense.
I'm sorry, maybe I cannot get the point of that question.
So go to your table where you have a bunch of benchmarks you ran. Yeah, so were there any other examples you tried which failed?
Actually, no.
Okay.
We designed some DSLs in our framework, and we found that all these DSLs satisfy the properties we want. And actually, maybe you want there are some number in here, and actually these sugars doesn't satisfy the fourth condition, and at this time we will have to introduce some auxiliary constructs.
Okay, that's what I want to know. Great, thanks.
Thank you. Other questions?
Hi, thanks for the talk. I didn't quite understand what was wrong with the disregarding of if of end. Earlier, you showed that it's leaked the abstraction. So, in the context of a lambda, right? So. Yes. So what was wrong with this disregarding? We disregard end into an if, right? Yeah. And then you said that if there's a lambda, you have a slide that shows the lambda x e. Yeah. Then you said something was wrong and the abstraction was leaked, but I didn't quite get it. Yeah. So yeah. Yeah, this one.
This page, right?
Mm-hmm. So what's wrong here, and how can you fix it?
Actually, this NF cannot be defined if a language doesn't contain if or and or any other similar functionality in the language. So what you want to ask is why this evaluation rule is wrong. Because this evaluation rule after we write an NF in the DSL program, and this NF will be evaluated to the right expression, and this contains an if. And this if is not the program, the DSL programmer writes. He doesn't write any if in his program.
Yeah.
Yeah, and in our example, we suppose that the DSL programmer doesn't know what is if. He only knows what is and.
So what's your solution? How do you fix this?
Actually, we want to say that this is a problematic syntactic sugar, and it's not the.
So you cannot disregard n into if.
To do this, we have to introduce some auxiliary syntactic sugars and to factor out this body. For example, we can define. Actually, I think I've.
Yeah. What's the solution look like?
Sorry. So we have to introduce the auxiliary language construct, this and f prime, and this n prime is same to the n, and we have to redefine this n f to use this n prime prime. And
okay.
Because this n prime prime we consider as a language construct of DSL, so DSL users can understand this. Yeah.
Okay. Thanks.
All right. Any other questions? All right. If none, let's thank the speaker again. So we are a little bit ahead of schedule. Let's give it a couple of minutes. All right, and the final talk of this session is on the exciting topic of getting the formal semantics from executable implementations. And Jenny Liu from University of Wisconsin-Madison will be giving the talk. On to you.
Hi everyone, I'm Jiang Liu, and I'm a second-year PhD student from University of Wisconsin-Madison. Today I will be presenting the paper Synthesizing Formal Semantics from the Executable Interpreters. We all know that formal semantics are great, and they can be used under many different circumstances. They can be used for verification, they are very useful for synthesis, and they can also be applied in static analysis. But there is still one big issue. They are too hard to be written for engineers. In fact, it is very rare that the program semantics are being actively designed by people outside the PL academia, and our tool comes for the rescue. It automatically synthesizes all this formal semantics given only the interpreter. So how does our tool work? To introduce that, let's just start with all the 3 example terms within the IMP language. We've got a atom term 1, we've got the plus sign, and we've also got the do while statements. So how do we create their semantics? The key idea is we use everything that is already available to us. We know that we know what symbols are allowed in the semantics, and we can write it down as a grammar, which is the syntax of semantics here. And we all know that there will be an interpreter that exists for the given language. The interpreter itself is capable of running any program under any input, and it just provides the output in return. Can we synthesize the semantics with only those alone? So let's think of the easiest way to do that. To generate many examples from the interpreter, and then synthesize the whole semantics with them. So here's the interpreter, which we already have. And we've got a bunch of example inputs and programs. So why don't we try to create a single semantics automatically that works for all these 3 terms? To achieve that, we tried to invoke an off-the-shelf solver, and then we failed. The solver just ran forever because the whole semantic function is too hard to synthesize in one shot. So what are the lessons we learned from this? To begin with, blindly generating all these examples doesn't help much in covering the full language. And the full semantic function is too big. So we shouldn't synthesize all the whole function at once. Instead, we should synthesize one for each of the term types and then put those together. And this naturally leads to our solution to the problem, synthesizing rule by rule. And this is actually our key approach. For the semantic function, which you can see in the green box, instead of synthesizing all those things, everything at once, we break it up and synthesize one rule at a time. So we can see the semantic function for IMP is broken into many, many rules, and there's one rule for each of the syntax constructs. So we've got one rule for assign, we've got another semantic rule for if then else, and another for the for loop. And here's our next observation. To introduce that, let's first have a look at the semantic rules for each of the 3 terms. So for the atom term 1, we can see there's only one output O equals to 1. And for the later ones, we can see although there are a lot of premises in each of the each of the semantic rules, they still share a lot of parts. And there are many parts that looks alike, which are the ones colored in blue. And those are the structural parts that are automatically deducted from the syntax, because we assume that the parent semantics, which is the parts under the line, it's always using the semantics of the child terms. And given all those semantic parts in blue, we don't need to spend time synthesizing them, and they will automatically go into the rule template here. So what are the rule templates? They're just used to put together what we already have, which are the structural parts, with what we will try to get, which are the red parts. we've already got the structural parts, and there are still some undefined parts in the semantic rule templates, which are colored in red. And those things are called the hosts. So what are the hosts? The hosts are just the first order logic functions that will become our synthesis target. In the whole process of doing the synthesis, we will only care about synthesizing the hosts themselves. And the structural parts are already given to us for free. And let's just here's our approach, just condensed into a flowchart. We first start by breaking down the rules into a bunch of rule templates, and then we'll use the example inputs, example outputs, and the programs to help with the synthesis of all these hosts within each of the rule template. The example input programs and outputs just come directly from the interpreter. After the synthesis, a candidate rule will be obtained and passed into the verifier. The verifier will test if the generated candidate semantic rule is truly correct, which means it's just doing the same thing as the interpreter, or if there's some discrepancy in the rule, which means the rule should be synthesized once another time to see if we can get a correct one. We'll then introduce the technical problem here we encountered by going through 3 examples. Let's start with the simplest. Getting the semantics of the atom term 1. So the language here is still the IMP, but we are only using one variable as its state. Here, the input state I is just a single integer representing what was the value before the whole execution. And the output will be another int, but it means the evaluation results of the single term. So the term is number 1, and we all know that whatever the input is, the output should be O equals to 1. And we have the F here, which is the whole we mentioned in earlier slides. The F stands for the whole function that relates the inputs to the outputs. And it is actually the only thing we are going to synthesize here for this rule template to get a complete semantic rule. So why don't we see how we synthesize F? To do so, we first extract all these examples from the interpreter, and as I've just mentioned, whatever the input value takes, the output is always 1. And we also know what is allowed in the semantics, written as the syntax of the semantic functions. And given all this information, we can then transform this into a syntax-guided synthesis problem. And there are a lot of off-the-shelf tools available. The answer is F equals to 1, and that's what we would expect. So why don't we come to a more difficult case? So for this case, it is more realistic because we're trying to synthesize the semantics of a non-leaf node. And the techniques for this case can be generalized to arbitrary non-recursive syntactical constructs. The parts in the green rectangle are automatically got from the syntax, because for non-leaves, the semantic function call to child terms are always needed because the parent semantics make use of them. Again, the F here is the whole that characterizes how the output is gathered from all those child terms. But here, we have 2 more hosts, the G and H. So what are they? They are the hosts for data flow. Those functions show how the inputs to the child semantics come from the input of the parent term, which is the I here. Given the child semantics here in the semantic rule, the next question would be how to express them. The child semantics may not be synthesized yet. It may use other types of unseen syntactical constructs, or even worse, it may use another plus sign which is currently being synthesized. So let's remember the key approach, one rule at a time. If we also ask the solver to simultaneously synthesize the semantics for the child terms while it is trying to synthesize that of the parent term, it will become too hard for them. So how do we get the semantics of the child terms, or at least a good and useful approximation to them, without actually solving for them? The answer is we use the examples again. The example terms and inputs will serve as a good approximation for child behaviors. And that is like what we've done with the interpreters in the whole process. And why do we do such an approximation here? That's because the examples will characterize the behavior of child terms. And if we've got all the possible input and output example pairs, that would serve as a useful and approximation for synthesizing the semantics of the parent term. And the intuition here is that even if a child's exact semantics is unknown, such an approximation would provide enough information for you to synthesize the semantics of the parent term. So let's just come through a concrete example on how we approximate the child terms semantics. Suppose that we've already got some child examples here, and we've also got the example input for the parent term, which is randomly generated. And we're going to synthesize the semantic rule of the plus sign. We use the examples here that is already available to us to approximate the child behaviors and synthesize the following functions to fill in the holes. However, this one is incorrect. We can all tell that the O here should not be equal to O2, but O1 plus O2 instead. Soon we notice that the reason for such a mistake is that the child's examples are not enough. Here we only have the behaviors of all these child terms when their input is 1 or 2, but not when their input is 3. So essentially, we don't know the behavior of the child term X when it gets the 3 as the input. That means O2 is not constrained at all. So the synthesizer treats it as a free variable, and a free variable can equal to any value, it just creates something wrong as a result. So how about adding the lacking inputs to the child examples? We just utilize the current data flow, which is I1 equals to I and I2 equals to I, to propagate the I equals to 3 inwards to each of the child terms example set. Now that we have the child behaviors when input is 3, we will try to synthesize again. This time, given the behavior of children on I equals to 3, we generated the correct semantics here. Let's do a recap on the example to know what we've done with a flowchart. We first generate the candidates F, G, and H, then propagate the inputs for child terms, and last we get the outputs for children using the interpreter. And we iterate again and again until we reach at the fixed point. The third example is about a recursive call. Overall, the problem looks very similar to the previous one. However, recursion itself brings another problem. How should we evaluate the self-recursive call? Fortunately, they can still be approximated with examples, but when should we evaluate it? We can't always evaluate. That will lead to infinite execution. The execution of the recursion here is governed by the recursion predicate, another function we introduce to control the recursion calls. The expected results are listed below. And when the recursion predicate evaluates to false, the recursion will not be executed. And for this case, we synthesize a different output function f prime. So in the previous slide, we introduced how we approximate child semantics and how we handle the recursive semantics. Then we will come to the implementation and evaluation. For the solving of Cygos and the SMT problems, we use the CVC5. And for overall algorithm, we implemented it in Scala. The benchmarks are from two sources, the SimGUS dataset and the previous work by Kalita. The SimGUS is a framework for program synthesis, and it enables the user to specify semantics of target language while generating new programs. And to test our synthesizer, To test the synthesizer, there's a benchmark set with all those problems and the semantics. To test our tool, we remove the semantics and use our tool to synthesize the semantics again. And we compare what we synthesized with the ground truth. The table here answers the first research question, the effectiveness of our tool. We try to synthesize the semantics of IMP, BV simple, which is big vector operations, and regular expressions. They all terminated within 20 minutes with the correct answers. Thus, we can conclude that our tool is effective on synthesizing semantics of non-trivial languages. And the second research question here is, how does the synthesized semantics compare to manually written ones? So for all but one languages, the synthesized semantics are the same. So there are two possible reasons for the exception. One, the algorithm is wrong, or there are issues with the semantics. In order to understand what's the reason here, we try to investigate the semantics. So the regex grammar, is the exception where the synthesized results differ. And we start by looking at the signature for semantics functions. The input of the function is regular expressions and a string of n characters. The output is a bunch of bool variables that shows what happens for every substring. By comparing the generated semantics and the manually constructed ones, we noted that some variables always take the same value, so we changed the signature to only use one variable for all this. And that means less inputs in the new semantic signature. Thus, when we try to synthesize the semantics again on the new signature, the synthesizer was faster because fewer terms will be enumerated. So let's do a recap. The main idea of this paper is the semantics can be synthesized from interpreters, and we do it rule by rule. We successfully synthesized the semantics of non-trivial languages, and we found better version of existing semantics. So there are some of the future works we have thought about. Do you know how to solve these problems? Please don't hesitate to come up with your ideas or questions. Thank you for your attention.
Thank you for the very interesting talk. We have time for questions. Georgia first.
Thank you for the very nice talk. I have a question about the template extraction. So is this step automated, or do you assume that the user provides the
Okay,
templates?
so thank you for your question. Your question is about whether the extraction of templates is automatic or manually done by the user. And maybe we haven't made it clear here, but it is fully automatic. We just scan through the all types of derivation rules that are used in the source language, and we manually derive one of this rule template for each of the syntactical constructs.
Hi, nice talk. Can you go to the slide where I started with implementation?
The slide of what?
The slide where the title is implementation.
The slide that's
which title is?
Oh, okay. Do you mean this one?
No, next. Experiment.
Okay.
Yeah.
Yep.
Previous one.
Previous?
Yeah, the list of.
Okay. Sorry, I'm just.
Yeah. Okay.
Okay.
So what I have seen from your talk, can you give me the algorithmic difference between the work you have done and the work by Kalita et al?
Okay. So your question is about what are the parts in the implementation that is done?
No, not implementation. The algorithmic difference, because the way you, so the Kalita the work done by this Kalita et al, which is me actually.
I'm sorry, I can't hear you clearly.
That actually, instead of doing full scale, it increments one by one, the way you do, and the way you merge things when these things doesn't work with the way you do it for child and all. So can you give me the difference from the algorithm we have implemented and what you have done? Because I couldn't get that one. It looks same to me.
Oh. Okay, so our work is different in several perspectives. The first is they are working on attribute grammars, but we are working on big step semantics. We are having a different objective of the synthesis. And the previous work by Kalita cannot characterize some of the semantic relations like the while loops, but our work can't do that. And we also we actually looked through all the benchmarks they used in their paper, and we found that most of their target languages are fully functional, but we use some imperative languages like AMP. So speaking of the expressiveness, we have much more expressiveness than their work.
Nope. And that's all time we have, so the rest goes offline. Let's thank the speaker.
Great. Can you test out your thing real fast? We've got 3 minutes. It's okay. Yeah. This. It should be. Hello? Hey.
Hello, hello, hello? Yeah, okay.
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 Oh, you good?
I have to check my presentation. Okay.
Okay,
Yeah.
good. And it's
Meghana.
Say it again. Meghana?
Yeah.
Okay. Very good.
Thank you.
Okay. Go for it. Go for it. Hello. We're in California. Everyone's friendly.
Right.
We just moved to Boston and PLDI was in San Francisco. San Diego. So I'm from San Diego. And everyone was going to say, it's crazy. It's like, everyone's like, hi, you know, how you doing, hon? It's crazy. You're like, what are these people trying to steal something?
Right, everything becomes very suspicious all of a sudden. Yeah.
New England changes you. Okay, I think we're getting started. Hello, everyone, and welcome to the first formal methods session of this year's OOPSLA. We've got an exciting slate of speakers this session. And to start off with is Andrew from Northeastern, who will be telling us about ABI.
Thanks, Ben. Can everyone hear me if I stand here? This is like a good position? Okay. So this is joint work with Zach and Amal, who are both also here, although I don't know if they're both here, but they're both at Splash. So if there are any unresolved questions at the end, please come and find us. We'd love to chat. So today I'm going to tell you about our approach for the formal specification of ABIs. But before we dive in too deep, I want to just quickly establish a working definition for what an ABI is, since it's not something that most of us interact with on a daily basis. I really like this definition from the Swift team, which says that it's the runtime contract for using a particular API. And this includes the usual things like layout and calling conventions, but more broadly, it leaves the door open for specifying the expected behavior of an API, which is an important theme that we'll see throughout the talk. Just as a little example, suppose we want to compile a small functional type from a higher level language. We have a variety of implementation decisions ahead of us. The particular ones aren't so important here, right? But maybe we decide to splat the input pair or pass it indirectly as a pointer, or maybe we use a return pointer. The key thing about these choices is that whichever one we pick sort of precludes compatibility with the other one. And that really brings us to the main motivation for using an ABI, which is interoperability. The situation is this. Suppose that we start with two source-compatible components, which we're going to style in blue here. Ideally, compilation to two target components, we're going to style them in orange, should be compatible as well. And the subtlety is that even if this happens to be the case for a particular compiler, the story gets much murkier if we decide that we want to link with code from two different compilers. And this is a really big deal. I mean, imagine if you had to recompile every binary on your computer every time there was a GCC update. It would be chaos. Adhering to a consistent ABI is one of the things that allows compilers to update independently. But it's not just about compiler updates. Other languages will use the ABI to build foreign function interfaces, which enables interop across different languages. And for example, we've all probably used a CFFI at some point or another. And speaking of C, historically, it has been sort of the de facto standard ABI. But recently, there's been this renewed interest from systems languages in designing their own ABIs. And I think the real reason for this is that these are languages with richer types that have very particular invariants about ownership and safety. And there's been a lot of, I'll say, spirited discussion about how much of that actually belongs in an ABI. And I think there are a lot of open questions in these threads, and I think the community would really benefit from a formal analysis of the ABI design space. But that begs the question, how should we actually formally specify and reason about ABIs? Revisiting this Swift definition, a particular API for us will just be a type, and the runtime contract for using that type can be defined as a predicate on target programs that behave like or realize that type. And in fact, this is just an instance of semantic typing, which is a technique that we understand fairly well in the PL community. But more specifically, it's an instance of realistic realizability, which is this term that was coined by Benton to describe models that are indexed by source types and inhabited by real target code. For Benton, these realizability models were proof devices that he used during compiler verification. But our proposal is not to reinvent the wheel. We can actually take these models and use them as the definition of an ABI itself. In order to evaluate the suitability of this approach, we've conducted a case study in which we compile, or in which we specify the ABI for a simple functional source language that we compile to a C-like target. And because we were very much inspired by the Swift ABI, we approximate a small subset of its implementation features, most notably automatic reference counting. And to make this specification concise, we define our realizability model using a separation logic with some new abstractions for reasoning about manipulating reference counts. Now, before we dive into the particulars of the ABI for this case study, I want you to keep in mind that this is just one instance of the general methodology. So at each step, we should expect the ABI to address both layout and behavior. Since our values are reference counted, that's where we'll begin our tour through the ABI. Physically, a reference is just some pointer L. But logically, a reference for a type T is characterized by this predicate R, which says first of all, that L holds a reference counter, C here, and moreover, that in adjacent memory sits an object that behaves like a T. And this is characterized by the object relation O. Whereas the reference predicate is uniform in T, the object predicate will vary based on T. So for example, as a simple example, an integer, right? An integer object is just some integer that's sitting in a cell, and we represent this using the points to connective from separation logic. Now that we know the basics of how references are laid out, we must also specify how they behave. A single reference represents one share to the underlying object, and likewise, multiple references represents multiple shares to the underlying object. And this establishes a lower bound on the runtime value of the counter sitting at L. Now, having a reference count confers permission to increment the count and acquire more shares, which we specify here using this Hoare triple. Here it says, given a reference at L, incrementing L will not only increase the count, but it will also produce two references. And these are joined together using the separating conjunction, which indicates that there are two distinct shares to the same underlying object. Going in the other direction, having a reference also confers permission to decrement the count, but the protocol for doing so is slightly more involved. Dynamically, we might learn that the count is still positive, which means that somewhere else out there, there's another reference that we don't have access to. And in this case, we lose access to the underlying object, at least through the input reference, right? And that's indicated by this empty permission in the post condition. On the other hand, this might actually be the last reference, in which case we learn that the count will hit 0, and we take back full ownership of the cell holding the reference counter and the underlying object. And in this case, we assume the responsibility for managing that memory. Now that we have a sense for how references behave, let's look at another object interpretation, this time for simple functions. Physically, a function is just a pointer to some function f. But logically, it isn't just any function. It must adhere to the calling convention for the type t1 arrow t2. Here the convention is again specified using a Hoare triple, which says that we must move in a reference to the input in order to call the function, and upon return we obtain a reference to the output. But this isn't the only calling convention one can imagine. Alternatively, you could insist that the function return a reference to the input as well as the output. The former would sort of be analogous to call or save, and the latter to call save, but in this case it's for references instead of registers. And both of these conventions end up getting used in practice. And separation logic is well suited for describing a variety of calling conventions, and we cover some more in the paper with additional features like recursion and closures. Now let's take a look at the object interpretation for structs. Physically, a struct just contains pointers to its fields, laid out adjacently in declaration order. So for this point example, it's x first and then y at offset 1. But logically, we know these aren't any old pointers. They're proper references to the fields. And remember that a reference holds a share to its object. And this in turn ensures that the fields live at least as long as the struct itself. Interestingly, this means that a struct may hold on to more memory logically than it does physically, since these field objects will live elsewhere in memory. To make this last point a little more clear, let's unfold the definition of R and rearrange things a little bit. So here we're grouping memory fragments by the object that they belong to. And in addition to these physical pointers that we had before, we're also using these thin gray edges to associate a reference with its object. Of course, the point object in the middle will most commonly be part of another reference itself, which may either be held by another object or by the root, as is the case in this diagram. Instead of using flat heap fragments, we use this graph representation to define the resources of our separation logic. More formally, we distinguish cells that hold reference counters from plain old data using these ghost tags, share and unique, where a share cell will contain the local share of the reference count and a logical edge to the object that it's counting. The advantage of using this representation is that it's really natural to define composition in a way that ensures that the total reference counts work out. For example, if we want to duplicate the point, we only increment the count at the root in a way that, and then the two objects between those two counters will have the same underlying memory. We don't duplicate the counts across the two of them. Likewise, if we want to duplicate a reachable reference like ly, we add the new reference to the root, and it points to the very same object as the original reference. Now, importantly, this is all just logical structure. The ghost tags are completely erased before we run any code. Resources that have this invariant, that the unique cells actually were unique, but the share cells will get collapsed, and their reference counts will be added together. In order to reason about these graph structures, we use two modalities that are loosely inspired by hybrid logic. The first is this jump modality at LP, which says that L is a reference counter whose object satisfies P, and locally it also confers one share of the object. As we saw on the previous slide, composing jumps together only affects the local count, and it does not increment any of the internal counts inside reachable objects. And in fact, all the references that we saw so far are just defined in terms of jump and the object relation. And so all those properties about duplicating references are actually just properties of jump. We also use the more familiar reachability modality, diamond, which enables non-destructive operations like reading and incrementing from deeply nested objects. For example, let's revisit the increment rule that we saw earlier, which we redefine in terms of jump. Instead of references, we'll have jumps in each of these positions. Using diamond, we can generalize the rule to allow incrementing any reachable counter. Here, the premise says that the precondition Q, somewhere inside of the resource satisfying Q, we can reach a jump to P. And we duplicate that jump independently without affecting Q, and that's why Q appears in the post condition as well. Okay, let's backtrack a little bit and revisit the definition of structs. This is the same definition that you saw before. You don't need to reread it. There, we decided to lay out the fields in declaration order, which is similar more or less to the way that C does things. And there's nothing wrong with this definition, but this sort of rigidity does have some implications for the ABI. For one thing, seemingly equivalent source types aren't necessarily ABI compatible. Since we're using declaration order, we can't reorder fields even if that's a natural thing to do in the source language. Moreover, these structs aren't extensible. Imagine that you're maintaining a library over a long period of time and you want to add a new feature. This ABI wouldn't allow you to add new fields in service of that feature. Let's be a little bit more precise about what we mean when we say the ABI doesn't support these updates. The situation is this. Suppose that we have a library that's providing types to a client, and we know that the components are ABI compatible after compilation. The question is, what updates can we make to the library without breaking compatibility with the original client binary? If you've ever found yourself in DLL or dependency hell, that's exactly the situation we're trying to avoid here. Through the lens of a realizability model, we can characterize the ABI-compatible type updates using semantic subtyping. Informally, this means that the new type refines the layout and behavior of the original type, so it doesn't violate any of the client's assumptions. Now, whether or not the ABI actually supports any non-trivial updates is entirely a design decision. So C, for example, doesn't support any type updates of this flavor by default, so library developers have to design their APIs in a little bit more of a careful manner. Swift has a very different vision that it calls library evolution, and they support a variety of type updates by default. This is something that we formalize in the paper, but I just want to give you a sketch for exactly how the techniques works, at least as it was devised by Swift. At the heart of the technique is what Swift calls a resilient layout. And the key idea is that rather than fixing the offsets of a struct, the ABI requires that they be available in a table that clients can query dynamically. Here, the client may only assume that the layout is consistent with the offset table, but it makes no other assumptions about the remainder of the layout. Then when a library actually implements the type, it provides concrete values for the offsets, which may include more fields than the client is aware of, and in a totally different order. Crucially, the library internally does not need to use this offset table because it knows the layout statically. But across a linking boundary, clients need to use indirection, which allows flexibility between releases at the cost of some runtime overhead. In the paper, we show that our ABI supports evolution for a variety of types and that it guarantees safety and memory reclamation. We also show compliance for an ARC compiler, which is sort of like the fundamental property for a logical relation. We also cover unboxed types and recursive closures, and we show how to express various type-directed layout optimizations that an ABI might want to support. For our next case study, we're currently looking at Rust, and we're working on an ABI with ownership and borrowing that we hope to define over WebAssembly. And the goal of this ABI is to verify an FFI, which is one important application of ABIs that we didn't cover for the case study in this paper. In summary, we've proposed a methodology for specifying ABIs using realistic realizability models, and we've exercised this methodology using a case study that introduces some new separation logic abstractions for reference counting. Thank you.
So we have time for questions. Just raise your hand, and George will bring you the microphone.
Yeah, so we're pretty careful in the paper to say that this is only a loose inspiration. It's world-ish in the sense that it does actually describe a node in the graph, and it does let you move between different nodes in the graph. But it isn't, formally speaking, a crypty structure, so it's sort of a loose inspiration, but it does have some relationship, yeah.
I can ask a question. So,
Okay.
So this was inspired by Swift, and I guess you're looking at Rust next. Can you talk
Yes.
a little bit about what the complexities of working with Rust or integrating Rust ABI into the system are?
Yeah, so I mean, one of them is just figuring out what borrowing means formally, which there's been a lot of good work on, but I think there's room to go. Another interesting thing as it relates to Rust is that there's a bit of a debate about how much of the borrowing semantics actually belongs in the ABI. So there's this Krabby RFC, and they do have a notion of borrowing, or they have a notion of references, borrowed references in the ABI, but they don't have lifetimes, So it's not exactly the same kind of concept that we're actually familiar with working, using in Rust. So we're trying to sort of navigate that space. Does it need the exact same abstractions? Does it need weaker abstractions? And that's something that we're trying to figure out. Yeah.
Very interesting. We have time for one more question.
Thanks for the great talk and the really interesting paper. I'm curious.
Is this on? Okay. I'm curious. I think Rust doesn't really have a definition of an ABI for sure yet. Right?
Yeah.
Could you maybe use your work in some way to assess whether one definition or another would be a good idea given the way people want libraries to evolve in practice?
That's exactly what we want to do, yeah. So there is a proposal where right now it's just a discussion, really, about if Rust wants an ABI and what it might include. And our hope is that by analyzing these things formally, we can offer them, like, here are the trade-offs behind different ABI decisions, and then they can determine, what is right for them in practice. Yeah.
This sounds great. Thank you.
Yeah, thanks.
Thank Andrew again.
Thank you.
Right on time. So our next talk is from Robert
Schenk
from
University of Copenhagen.
DIKU, right? Yeah, Copenhagen. Yeah.
All right, I'm Robert, and this talk is about AutoMap. And if that means nothing to you, it's roughly how can you do NumPy-style broadcasting in a statically typed language. And it's in collaboration with all these people. Martin is here, if you want to also ask him questions that I can't answer. And everybody else, we're all from Denmark. So to start, you might have an operator plus to add two numbers together, and it just does this obvious thing on two scalars. But we might also want to add two vectors together with the same operator. And of course, it should just add them component-wise like you see here. Or we might want to add a scalar to a vector. And then we would broadcast the 4 into a vector itself, and then we would add the two vectors together to get this result. And of course, this isn't only just for binary operations, it should also work for unary operations. So here we have the square root thing, and we can apply the square root to a matrix, and we want the square root of every element in that matrix. And so the question is, how can we accomplish this in a static type system? And what this is sort of roughly called? Oh, sorry, okay. And what this is called is called rank polymorphism, which is sort of the ability to apply functions to arguments that have different ranks than the function sort of naively expects. And this is mostly sort of a syntactic sugar type of thing. It just makes code nicer and easier to read. So for example, on the left here, we have what you would normally do in a language where you have to manually apply this map to addition across two vectors. And it's much nicer just to be like, hey, we have this vector, let's just add them together, and you can apply the operator infix, which is also much nicer. And in practice, pretty much every language that can do this happens to be dynamic. And so this talk is, how can we do it in a static system? And just to get started, let's first review how map works, which I think most people here know, but all map does is it takes a function f, and it takes some vector, and it applies f to every element of that vector. And our map is special in that it can take multiple arguments. So you can take, for example, here we have plus, and we have two vectors, and it just does a component-wise addition between each component. We also have this thing called rep, which is like replicate, except you don't specify how big the thing is that you want to replicate, so it just makes some number. You can just think of it as increasing the dimension of the argument. So for now, we don't really care about how many elements are needed. In the actual implementation, we can figure it out in some ways, but this talk doesn't really talk about that. But it's a solved problem, so don't worry about the fact that we don't know how many elements we want for now. So an example of how this can work with map and rep is, for example, here we have a matrix, and we want to add a scalar to it. So what we first do in this elaboration is we rep the 1 twice to sort of boost its dimension twice and get a matrix of 1s. And then we map twice to lift addition up 2 dimensions to work on matrices. As another example, here we have 2 matrices, XSS and YSS. That's what each bracket there is a dimension, and then the underlying type is an int. So it's 2 matrices of integers. We have some function which takes a vector, a matrix, and it gives you back an int. And now we want f of xs, yss to work. And right now, of course, this is ill-typed. But what we can do is we can first map this f across both matrices. But now you've noticed that f as its second argument, it expects a matrix, but if we're mapping the F, and now it needs something that has rank 3, so we have to also rep the YSS matrix to make this thing work. And also in practice, these reps are free because you can actually push this thing down into a lambda, and then you don't actually have to do actually implement the rep in practice. So our goal with this work is for any function application, the compiler should automatically insert these map and rep operations to make the application so-called rank correct. So what this looks like is we have some application here, f of x. We want to figure out how many maps and how many reps do we need to make this thing actually type correct, or at least rank correct, which is the first step to being type correct. And there are a number of challenges involved with this. So here is one example. So here we have a sum function, which expects a vector, and it tells you the sum of all its arguments. And we have this length function, which is polymorphic. So it says for any array, tell me how long it is. And we also have this matrix. And now we're saying, what is the sum of the length of this matrix? And there are many possible rank correct elaborations here. So for one, sort of the naive thing is, it's a little bit weird, but you can take the length of the matrix, and you can replicate it to boost its dimension. One that you probably like more is this is first mapping the length across the matrix. So then we have a vector of length, and then we take the sum of that. But there are, of course, many more options. In fact, there are infinitely many more options. And a question that this work has to answer is, how do we choose which option? So part of that strategy is that we have this rule 1, which is that an application can be mapped or repped, or neither, but never both. So just to show what this means, this is, of course, OK. You have one map. This is also OK, because you can have multiple reps. You just cannot have a map and a rep. And this is also OK, even though it looks like it might not be OK, because it's actually two applications. We're first applying h to x, and then we're applying that whole thing to y. So it's actually two separate applications. So this is also legal under rule 1. But what isn't OK, for example, in this first example, we're applying map and rep to the same application. Or, again, the same thing in the bottom, just with multiple maps. And it turns out it's never necessary to map and rep in the same application to attain a rank correct program. So if you can get a rank correct program, you don't ever have to do it both. So this is a fine rule to have, and it also reduces many of the possible options that an elaboration could be. As another way to reduce the number of options, we want to minimize the number of maps and reps that we insert to get a rank correct program. So this has multiple benefits. First, it usually aligns with what programmers intend. We tend to write the absolute minimum number of maps and reps in practice when we write code. And it also makes for a simple mental model. So it's very easy to communicate to programmers how the elaboration will work. You just say, that's the minimum number, and it generally aligns with what they would do anyways. And importantly, though, that this minimization is over all the applications for top-level definition. So you can have, you define some definition on top level of your program, and there's a bunch of applications in it. And what we're doing is for every single application in the whole program, we're saying find the minimum across all those applications, not just individual ones. So it's actually a global minimization, at least at the definition of top-level functions. So if we go back to our sum length example, these are what we saw already, and we saw also these ones, and now we can eliminate those options. So now we've reduced the possible options to just these two. But another challenge here is that the elaboration is so-called global. And what I mean by this is, so in this first example, when we did the rep with the sum, we used sort of local reasoning, which is we applied length of xs, that works, that type, so we don't do anything. And then we tried to apply sum to this thing, and we go, oh, the dimension is too low. And so then we just insert a rep. So we're sort of considering each application one by one. But in the other example, when we use the map, this is sort of an instance of global reasoning in the sense that length xs is in itself rank correct. But if you also think about the outer sum, then you can sort of preemptively insert this map there because of the outer sum application. So what this really means is that we have to actually consider every single application all at once. And that is also another challenge. And yeah, another challenge, I forgot to mention this is about free thread, but I'll get to that. This is the type system in question has parametric polymorphism, so we have type variables. And that makes things quite challenging because a type variable can have any rank. So we have no idea what the rank of this thing should be statically, and we have to sort of make a decision in that regard. And so we have this question of how can we statically insert maps and reps in the presence of type variables whose ranks are not known. And the way that we do this is with a constraint-based system. So suppose that we have this function. It takes some parameter type p, and it outputs some type b, and we have some argument of type a. So we're considering the application f of x. So in this application, we have this constraint, namely that the parameter type should equal the argument type. But in our circumstance, we only care about the rank. So we're going to relax this constraint to say the rank should be equal, where this double bar thing just means the rank of P. So for example, if we have this matrix type on the bottom there, the rank of this matrix is 2 because there's 2 brackets, and the rank of a scalar there, the int is 0. So in our context, we want to allow rank differences, right? That's what rank polymorphism is sort of all about. And the way that we can do this is, so there's 2 cases. The first case, so I'll remind you that P there is the type of the function argument, and the A is the type of the T there is the type of the function's parameter, and the A is the type of the argument. So you can imagine that the rank of the function, what the function expects, is less than what you've given it. And in this case, we can introduce this rank variable, m, which is suggestive because it's going to correspond to a map. And then we say that instead of having the equality before, where we want strict equality, we're going to relax the equality and allow difference via this rank variable m. So what this looks like in practice is we can have, for example, the square root function, which expects a scalar. And we can apply it to this vector. And when we apply to the vector, and we look at the constraints, this says that because the argument there that expects is an integer, but we've applied it to this vector argument, we have this m plus 0 equals 1. So we find out that m equals 1. And of course, indeed, this would be rank correct, right? You can map the square root across the vector. And sort of dually to this, you can have the other case where the argument type is less than what the function might expect. And we do the exact analogous thing, except we have this rank variable r for replicate. And in this case, we're going to consider this example of length. It's a little bit weird to do the length of 3, but it's just to illustrate how this works. And this would then yield this constraint. And interesting here, though, is that this b here right now actually is a type variable. And type variables can have any rank. So this actually has an infinite number of solutions. So one possible solution is we say there should be r should be 1, and then b can be equals 0. But of course, we can say r equals 2, b equals 1, and so on forever. So there are actually an infinite number of solutions here. All of these are sort of rank correct. And then sort of to summarize this constraint-based approach is, so for every function, every application of this function, so of a function of type from P to C to an argument x to A, we'll have this constraint, where we've sort of have both m's and r's, because statically we don't know if the argument will be underdimensioned or overdimensioned or neither. So we have to account for all possibilities in that regard. Of course, we also have this rule, which we said that we can either map or rep, but not both. And so we also have this additional constraint that says either m equals 0 or r equals 0. And what we then do with these constraints is, so we collect exactly these constraints for every single function application and top-level definition. So let's, again, look back at sum and length. These are the constraints for length. And then these are the constraints for sum. And then, as you might imagine, we also had this rule 2, which said that we wanted to minimize the number of maps and reps. And you might be able to see what's coming. That is exactly saying we're minimizing these rank variables that we've introduced. And this looks exactly like an ILP. The only thing that's not an ILP about it is the fact that the ORs are not linear, but you can linearize these constraints in practice using a little trick, but I won't get into that. So the way that the system works in summary is, so for every application in a program, we generate these rank equality and rule 1, which are the OR constraints. We transform these constraint sets into an ILP and solve the ILP with an off-the-shelf ILP solver. And then we use the solution to the ILP to actually elaborate this program. And when I say elaborate, so you can think of this application of X as having implicit maps, and now we're making those explicit. So here we found out that in this example, m was 3 and r is 0, so that means there's 3 maps. And then we have this program which is completely elaborated. You can sort of think of it as it's not rank polymorphic anymore. And then you can just type check the elaborate program as usual and then continue with compilation. And the rest of the compiler can be totally ignorant of the fact that it supports rank polymorphism. So user experience-wise, map and rep are just normal source level functions. The program can just write them as much as they want, which means you can choose how implicit you want these things to be. You can insert them to any degree that you want, and you can choose to use the auto map system or not at will. There's also good ambiguity feedback. For example, there's no way to completely remove all ambiguity in all cases. So in this case, the compiler can't decide. So, but it's easy to show the user what the options are. You say, these are the options. You should choose one. And the way that they choose is to just insert either the rep or map themselves into the source level program. And of course, it's fully transparent. So you can have a program with implicit maps and reps, and you can be like, hey, tell me what it actually should be, and how it will actually elaborate. And the compiler can spit out the equivalent program with all maps and reps completely elaborated, so you can see exactly what's going on. So for the practical impact, so we've actually implemented the system in a language called Futhark, which we developed at the University of Copenhagen. It's a functional array language. It supports parametric polymorphism and top-level let polymorphism. Sort of difficult to quantify the usefulness of a feature which is just syntactic sugar, but what we did is we have a very large benchmark suite, and we took away maps whenever we thought it made it better. So as an example of this was a program in our benchmark suite, and it has a bunch of maps. It's kind of hard to see what's going on. It's kind of also hard to see the relation to the original math that this is actually implementing. Don't worry about the details. You can just see it's kind of a mess. And with AutoMap, it looks much closer to the actual sort of mathematics that we're trying to implement, and it's much cleaner and easier to understand. And average, so I'm running out of time here, so I'll just be fast, but this resulted in a compiler slowdown about 2.5 times, which isn't great. It's very unoptimized as is, but in practice, it's quite usable, even though we're solving many ILPs during type checking. And so in summary, AutoMap is a conservative extension of a Hindley-Milner style type system for array programming. Anything that can be inferred can also be inserted explicitly. So this is just like a classic type system, right? You can always insert a type annotation yourself, or you can have it be inferred. There's just sort of dual to that. We use some heavy machinery named ILP solvers, but the ILPs themselves are fairly simple, and in practice they're solved quite quickly. And while it is implemented in Futhark, it's not really production ready yet. So there's some existing work to be done, including speed, better ambiguity checking, and better feedback to the user. And that's it. Please check out Futhark at futharklang.org. There's a blog post that covers everything I talked about in much more detail. The paper is also there with a full formalization, and these slides and more about me can be found out on my website there.
Thanks for the great presentation. It was really interesting. So can you go back to the previous slide? Actually regarding the third bullet point. So did you look into features which are available in type systems of the languages like Scala, which is basically the implicit conversion and these kind of things? Perhaps actually you could kind of embed something similar in house languages like Scala with their type system. Have you looked into it?
I have not, but a reviewer also brought this up, but I didn't understand their question. So I don't quite understand yours either. Maybe we could talk about it after.
Yeah. I think that would be great. Thank you very much.
Yeah, so I'm not an expert in this stuff, but so I assume systems like NumPy do some kind of dynamic policy.
It's just all dynamic, right?
Yeah, so I'm just wondering
the issue of really what makes this whole thing hard is the type variables.
That's okay. So I was just gonna say, given the same program, you could do it in NumPy or do it using your thing, and I'm just wondering how these two policies, the dynamically determined one and the static one, would compare to each other.
So in NumPy, there's no, as far as I can tell, every implementation of an operator can do it differently. So there's no hard and fast rule. It's not that principled. This approach is, from what I understand, is much more principled than how NumPy might do it. You can also see what happens before you've run the program, right? Whereas in NumPy, it happens dynamically.
Thanks for the talk. I think it's super nice to see the verbosity kind of disappear. What I'm wondering is, from a usability perspective, when you are trying to debug your program, having so many things implicit and automatically inserted, how does this interact with that? Do you have any insights or experience?
Yeah. So there's always sort of this conflict, right, with implicit stuff. Is the more that you have implicit, the more that things can become ambiguous, right? So you've sort of changed the space of what this program can be. And it's just like in programming languages, very sophisticated type checking, in the sense that the way that you debug these things is sort of you insert manual type annotations until you sort of figure out where is this bug. And in AutoMap, the way that you debug it is you insert manual maps and reps until you sort of identified where the problem is. But in practice, we've actually found it quite usable and quite pleasant, and we've also found it that when we write something implicit, it almost always elaborates to what you would want to elaborate. So there was good alignment, and the quality of the programming experience is quite similar to what we already know with static type systems.
So can it handle something like adding 2 vectors of different lengths to infer, or?
That would no. In practice, that would result in a size error. Which I didn't talk about in this yet, but.
Thank you for the talk. So I'm curious how you guys decided to choose the term rank for this, because it means something else in like the Haskell world, and I guess like higher rank types and stuff like that.
You said length?
Rank.
Oh, rank. Yeah, rank just means the number of brackets in front of the type there, basically.
Right, but
yeah.
isn't that like a clashing definition with how it's used in other?
Oh, I think I think you're thinking of higher ranked things, right?
Yes.
Yeah. I know there are many things called rank, but that's specifically higher rank polymorphism and not rank polymorphism. But I did not choose this terminology. This is existent terminology. Like it's old.
Oh, if it's an existing term, yeah, of
it's
course.
old stuff with like APL. You know, it goes way back.
Oh, okay, cool.
But I agree, it's confusing.
Thanks.
We do have time for one more question if we have one.
So you mentioned you had a benchmark, and you sort of took out some of the explicit maps, and then you went to see if like it put them back in.
Yeah.
Did you actually do a systematic evaluation of like erasing them and then having automap, insert them and then comparing the programs? Did you find that it would insert the original ones more often than not?
We were a little bit lazy with this, and we checked to make sure that the benchmarks because they all have outputs that you expect, right? And we checked that all the outputs are exactly the same.
Okay,
So we
that's
assume
good.
that with high probability,
Yeah.
it's very unlikely that you'd get two things that are not actually equivalent and had the same outputs.
Okay, yeah, that's pretty promising.
So
Yeah.
we're quite, and we did it for the entire benchmark suite.
Great. Okay. Awesome. Thank you.
Okay, our next speaker is Noam, who's going to be talking about a cool logic that marries sort of over-approximate and under-approximate reasoning. So, take it away.
Yeah, thank you. My name is Noam Zilberstein, and so I'm going to be talking about outcome separation logic. And this work was joint with Angelina Saling and Alexandra Silva, and all of us are from Cornell. So the key question in this paper is, can a single algorithm handle both verification and bug finding? And so to begin to answer that question, I first want to say a few words about what incorrectness is. So all this incorrectness stuff is kind of spurred by incorrectness logic, which was introduced by Peter O'Hearn in 2020. Of course, he didn't invent incorrectness, but he did identify these two properties of incorrectness analyses, which are very important in terms of practical implementations of bug finding tools. So the first one is true positives, which basically means if your bug finding tool says that there's some bug in the program, that behavior should be something that is actually realizable by a trace of the program. So we'll see in a minute what that means. The second one isn't so much a soundness concern, but more an efficiency concern. So under approximation basically means that you should be able to find bugs without inspecting the entire program. And that makes analyses more efficient because they can just kind of go down certain paths that look fishy. Okay, so let's look at what do bugs look like. Here, this program has a bug. This is an incorrect program. Why is this program incorrect? Well, malloc is non-deterministic, so malloc may return null. And if malloc returns null, then this memory dereference on the second line is going to segfault. Okay, so let's see what happens if we try to specify this bug using a standard program logic like Hoare logic. In Hoare logic, the post condition applies to all possible end states. So the best we can do is basically use a disjunction to say that there are two states that we could end up in. Either the execution succeeds and x points to 1, or the program crashes because x is null. And the question is, does this actually characterize the bug? And the answer is no, because we don't actually know that the error is reachable. And so to kind of demonstrate this further, let's look pictorially at what this specification looks like. Okay, so in Hoare logic, you kind of get a precondition and a postcondition, and so we can represent this in a picture by showing the blue circle represents the precondition, the green circle represents the postcondition, and what the triple says is that if you start in any state in the blue circle, then all the behaviors of the program end up inside the green circle. And so the program we were looking at has two outcomes due to non-determinism. One is the OK and one is the bug. And the question we ask is this bug possible? And the answer is not necessarily, right, because we could actually substitute in a different program that also satisfies this specification, but it doesn't have any trace that hits the bug. So we don't know. So in the solution that we use in outcome logic to address this problem is to say, well, why should we just get one circle to draw around all of the possible end states? We should basically get a circle for each reachable outcome. Okay, so we can draw a circle around each of these non-deterministic behaviors, and we say each of these things are reachable outcomes for the program. So what that looks like formally is in outcome logic, we have triples, very similar to Hoare logic, so we have preconditions and postconditions, and the meaning of these triples is that if you take a set of states that satisfies the precondition and you run the program in all of those states, then then the set of states you end up in satisfies the postcondition. So the important distinction here is that the pre and postcondition are now satisfied by sets of states rather than individual states, which is going to allow us to talk about the branching structure of the program. And to do that, we have these assertions called outcome assertions. So we have some typical constructs here like conjunctions and disjunctions, and then we have some new stuff. And so the first new thing is this O+ operator, which we call the outcome conjunction. And what this basically says is you can take the set of states and divide them up among the two assertions, phi and psi, so that some of the reachable states are satisfied by phi and some are satisfied by psi. And we'll see in a second an example of what this looks like. And then the second construct I want to point out is just the kind of the basic atomic assertions. So here, if you write P, where P describes some set of program states, what this means is that P describes all of the reachable outcomes, but also that there are, the set of outcomes is non-empty. So we know that this is actually a behavior that can be reached. Okay, so we can now use this to specify a bug in outcome logic. So what we've done here is we basically just replace the disjunction that we saw earlier with the outcome conjunction, and that tells us that these states are reachable. So we now have a guarantee that this error, that there's actually a trace that gets to this error. And then, so this is the true positives property that I mentioned at the beginning. We know this error is not vacuous, but we kind of have a problem because we're not meeting the under approximation guarantee, because if we wanted some some analysis that would find this bug by only looking at a portion of the program, it's not obvious how we would do that with a specification like this, right? So we're recording this outcome that is not really relevant to the property we want to express. And to fix that in outcome logic, what we basically do is we rearrange the postcondition, and we just replace the outcome that we don't care about with top, where top is a vacuous assertion that is satisfied by any set of states, including the empty set. So what this specification says is that the error is definitely reachable, but then there could be other outcomes too. There may not be, but there could be. And so if we go back to the picture, what the new specification is saying is basically there's this transition, there's this behavior of the program that is non-vacuously satisfied by a bug, and then we took all the other possible end states, drew a big circle around them, and just said, we just said true, so there's kind of like no information. Okay, so this is kind of how we can use outcome logic to specify bugs, but the next question is, how can we use this to develop analysis algorithms? And to answer that question, I'm going to kind of use Infer, the Infer tool, which is developed at Meta as a case study. So the classic algorithm of Infer was really a correctness algorithm, and it reported results in terms of Hoare triples, where the precondition would be some start state, and then there would be a big disjunction of end states, which, due to kind of abstract interpretation, it would be possible to merge some of these disjuncts, but if for maximum precision, you would record all of these things. And then more recently, Infer has been adapted to also have an incorrectness or a bug finding mode called Pulse. And what Pulse does is it represents bugs using incorrectness logic, where the postcondition is just referring to some reachable outcome. And so the issue with this is that we're now reporting two different types of specifications and two different program logics that are semantically incompatible, so they can't really be used as part of the same tool. Whereas in outcome logic, we can create similar algorithms, but where we give both types of specifications in the same logic. So the correctness specifications, again, enumerate all the reachable outcomes, but now with outcome conjunctions so that we know that they're reachable. And the incorrectness specification drops information about the non-erroneous outcomes. And so there is kind of a common denominator between these so that we can use the same algorithm for both. Okay, so now I want to talk about how do we actually build algorithms that do this, and in particular, compositionality. How do we get compositionality, which is kind of the key to effective program analysis? So program logics already give us some amount of compositionality, sequential composition, so that when we have a program that's composed, or it's a sequence of two smaller program fragments, we can analyze the program by analyzing each fragment on its own. The problem is that these specs that we see here in the premise of the sequential composition rule might be pre-computed, right? So we may not want to actually go back and reanalyze the procedures that they refer to. And then the particular problem is that the pre-computed specifications may not actually match up, right? So the post-condition of the first one might not match the precondition of the second. So the question is, how can we use this rule given pre-computed specifications? So one thing we can do is we can use separation logic, which gives us an additional type of compositionality, which is spatial compositionality via the frame rule. So what the frame rule basically says is if you have some local specification that's only talking about the specific memory footprint that the procedure uses, then you can augment that with information about other parts of the heap. So that's great. And so we've added to outcome logic the ability to use the frame rule and spatial compositionality. And the way that kind of works is that when you have a bunch of outcomes and you want to apply a separating conjunction to them, the separating conjunction just distributes inside of all of those outcomes. So you can just add the frame to each individual outcome. Now, the reachability of these outcomes did present a bunch of soundness issues. Well, not issues. They were solved in the paper. But it was very non-trivial, very subtle. So I'm not going to get into all the technical details, but I'm happy to talk about that offline, or you can check out the paper. Okay, so what does the frame rule allow us to do? Well, there was this work on biabduction, which is now about 15 years old, which it provides this procedure for reconciling two separation logic assertions. So if you have some P and some Q, and you want to know how can I sequence these together, biabduction will find the missing anti-frame and leftover frame that you can add to these two things to make them to make the first entail the second. And with biabduction, we can create a new sequential composition rule where the two pre-computed specifications don't match each other, and we use biabduction to find these pieces that we can add to them with the frame rule to make them go together. I mean, biabduction isn't guaranteed to work, but in practice, this has been a very successful technique. The thing is, so we can use biabduction in outcome logic, but outcome logic has additional forms of compositionality, or additional types of composition, namely branching. So if you have a program that branches into two outcomes, so here C1 and C2 represent two non-deterministic possibilities, two non-deterministic paths that the program could take. Now we have a similar rule where we would want to analyze this type of program compositionally, but what if we only have pre-computed specifications where the preconditions don't match? And to solve that problem, in this paper, we introduced a new entailment procedure, which we call triabduction. So triabduction is similar to biabduction, but there are now three unknowns. So you have a missing frame still, and then two leftover frames that you have to find. And the way that we use this is we can create this branching composition rule with triabduction, where we have our two pre-computed specifications. We use triabduction to find the precondition that's kind of like the common precondition among them, and then we can add the leftover frames to the two postconditions. So this allows us to analyze branching behavior compositionally. It also solves another problem with biabduction algorithms, which is that most biabduction algorithms have to analyze the program in two passes but try abduction actually allows you to analyze a program in a single pass, which is quite nice. Okay, so let's see how can we use all these ideas to write algorithms that analyze programs for both correctness and incorrectness. So this is kind of going back to the example I had at the beginning. Here we have the malloc procedure. As you would imagine, malloc is a very commonly used function. So it's going to be used all over the place in your code base for both correctness and incorrectness. And so it makes sense that we would have some maximally specific specification for it that specifies all the reachable outcomes. But from this, we can derive two new specifications by just dropping the respective outcomes. And if you were writing an incorrectness analysis, you may use some heuristic to say, well, if X might be null, that's kind of a suspicious situation. So we could select that specification and use that in a sequential composition with the next command, which we saw before. And here we would see that if X is null and we then execute a memory dereference, the program will crash. And then the true outcome, we can just kind of push it forwards using a vacuous rule because this triple with both pre and post condition of true that specification holds for any program. And then we get the bug specification that we saw at the beginning. So with that, I'm gonna conclude. So we saw how outcome separation logic allows us to witness the reachability of many outcomes. And because of that, we can use it for correctness and incorrectness. I didn't get into this, but the algorithm we have in the paper actually also works for probabilistic programs. So that's pretty nice. And all of it's powered by local reasoning with the frame rule. And so using try abduction also, we were able to create compositional algorithms for these programs with branching and reuse specifications. So now I'm happy to take questions.
Can you just say one more sentence about probability? Like, so
yeah.
Does O+ operate over distributions instead of sets?
Yeah, so you can think about you can think instead of O+ being like dividing the set of states, you can think about more generally that there's some sort of like mass of a collection of states. And so you could think about that like a set where you divide it, but it could also be like you're dividing up the probability mass. Yeah.
Thanks for the talk. So to my understanding, and I might have misread the specification here, but for your triples, you're saying for all states in the precondition, each state must satisfy all of the outcomes in my post-condition, modulo whatever, like algebra your outcome. So like say non-determinism if you're doing sets. How does that work with your claim that you can do under approximation? Because then I'd assume for something like a loop, you still need to prove for all states that every single state can reach whatever outcome you're interested in. So you can't say for only like some unrolling of the loop that they satisfy that outcome.
Yeah, so okay, so first of all, under approximation can mean several different things. Like in the incorrectness logic literature, what they mean is, in Hoare logic, we say that the post condition over approximates the strongest post, and in incorrectness logic, it under approximates the strongest post. Here, it's a subtly different understanding of under approximation, where we're saying we're under approximating the set of reachable states by kind of ignoring some of them, or by like vacuously satisfying them by true. So you can do similar stuff. Like if you wanted to analyze a loop by doing bounded unrolling, so you just unroll like n times for some fixed n and then stop, you can still do that. So in incorrectness logic, if you want to do that, you kind of need to have the information about why the loop stopped in the post condition, because the post condition has to be very precise. Everything in the post condition must be reachable. So you can kind of do the same procedure with outcome logic. It's just that the information about why the loop is going to stop has to be in the precondition. So it's sort of the same information, it's just where you're specifying it. And actually, the algorithms that they've implemented at Meta inside of Infer that they've implemented for incorrectness, they actually specify those conditions in both the precondition and postcondition. So it's interesting because you can actually interpret those triples as either incorrectness logic or outcome logic. So yeah, I hope that answers your question.
That was a great talk. I learned a lot. So I have a question about your treatment of non-determinism. So I think normally I never care about this, but in your logic it seems to matter, which is your non-determinism is binary, meaning it has two choices. And it looks like your choice rule uses those two choices. What if the non-determinism comes from guessing the length of an array or something that is basically not a finite area operation? Like, do you have a rule that can handle that, or what would you do?
Yes, yeah, so we use some programming language that has this binary choice operation, but we're also, I mean, maybe not in the exact formalization from this paper, but in general, we would allow you to kind of add your own atomic actions. And so you could have some atomic action that has like infinitary non-determinism. There are issues with that if you want to do total correctness. So unbounded non-determinism doesn't work well with total correctness. But if you only want partial correctness or incorrectness, then you could do unbounded. And then, I mean, the outcome conjunction, the like O plus, is kind of binary. You could have an infinitary one, but it depends what you're trying to do. Like, if you want the postcondition to be like finitely representable, it may be an issue, but yeah.
Actually, one last question, Jeff.
Okay, hey Noam, great talk. If I remember correctly, with biabduction, there's usually more than one sound solution, and so many algorithms decide to approximate because it is a very infeasible problem in many cases. Is that more difficult with triabduction?
So we use some of the same tricks where, like in biabduction, one assumption they make is if you have if you have x points to something and y points to something, they assume that x and y don't alias each other just to cut down on the space of solutions they need to do. So we kind of use the same heuristics as in biabduction because that's what has been shown to work. But yeah, I mean, triabduction also has many possible solutions. So we try to come up with like a minimal one if we can, but yeah. Thanks.
Let's thank Noam again. You can also move the microphone. So our next speaker is Jeff from Texas A&M, and he'll be talking about recovering variable and type names from bytecode of smart contracts, hopefully.
Looks like it's not displaying. Let me check. One second. Looks like not.
Maybe you could mirror it?
Yeah, that's what I'm looking for.
This is Mac?
Yeah.
Okay. Go to display.
Pretty old Mac.
No, bro, go to display. Okay, I'll tell you the simplest thing.
Oh, cool.
Very good.
So, yes, I can do this.
Very good. Okay.
Make sure this all right. Well, thank you all for being here. So this work is a collaboration with Wei Song and his student Yi Chen Li at Nanjing University Science Technology. Apparently, they did most of the work. Unfortunately, they cannot come here to present this work. So, you know, if there are some questions and very low-level detail I cannot understand, feel free. You know, I'm going to pass to them. Okay. So this talk is really about smart contracts, blockchain. I wondered how many people are familiar with blockchain here. Right, great. So it's going to be interesting to you. So, you know, blockchain has been there for, you know, more than 10 years, 15 years since I think the Bitcoin paper. Lots of programming efforts have been developed for writing applications that run on top of blockchain. There are a bunch of applications, right? So as of today, now, if you look into blockchain, you'll find, the many blockchain applications are written by Solidity, this language, but without source code. If you go to blockchain, you find, those are just binaries, okay? Unfortunately, this actually becomes a more and more important problem these days, because without source code, it's very difficult to understand some, malicious behaviors of those, smart contracts. Let me try to give you some example here. So a blockchain application would be something like this, okay, be executed by a virtual machine. And as you can imagine, all types are lost, right, when you're having something like this. Trying to go through the compilation process of a Solidity smart contract with you and show you how the types are lost in this compilation process. So on the left-hand side, this is very tiny, simple Solidity source code. Okay, and then in the middle, it's basically the steps that a compiler would do. And right-hand side, this is the binary code corresponding to the assembly code. Okay, so given the source code, it first does lexical analysis. Okay, and then it removes types. Essentially, all types on the binary level become a 32 bytes of data, right? So you really don't know what's going on with with that data. And then you assign variables to storage slots. So you're going to see something like this. And then, of course, there's intermediate representation that compiler will do all kinds of optimizations, right, trying to reduce the gas cost of something, right? So today, the Solidity compilers, they are optimized, trying to make execution cost as low as possible. Okay, that's one of the major contributors to this type missing part. Okay, so at the end of the day, what you see is something like this, right? You see a lot of hexacode, but imagine you are a security auditor, right? And you're given a piece of code like this, and you ask it, hey, is this potentially malicious or not, right? Reverse engineering, this community has been doing all kinds of reverse engineering, in particular security, right? It's very heavyweight in this context. So in the past few years, there are a couple of decompilers, being developed, on smart contracts. I think this called Panoramix is one of the most popular one. If you go to EtherScan, where you see all kinds of smart contract, you'll see this is a built-in decompiler. So if you take the source code, it would generate, it would take the bytecode, it would generate some source code like this. This is another one called Ali Plonk decompiler. So this is that developed by a startup. I think some of our colleagues here co-founded. I think this is probably one of the most sophisticated decompiler for this type of tasks. So when we look at this, we found, actually, with all these great decompilers, the capability of them for recovering types from the Solidity bytecode is pretty low. So we look at this precision and recall, you'll find less than 50%, for Panoramix. and even lower due to some reasons for a leap mark. Okay, so this work develops a tool called var lifter. This is actually pretty much interesting in terms of technical part. I introduce later. Okay, it's achieved very high results in terms of type recovery. Okay. And you may wonder how about large language models, right? And think about OpenAI. This is a few hundred companies in the States valued $150 billion dollars. What is the best model? Can this model be used to recover types, right? We tried with GPT-4o. As of June 2024, and we found, GPT-4o was not good, doing this type of work. So it's below 15% of precision recall, and with all kinds of, prompt engineering, we tried. Variable alignment is still less than 20% of, precision recall here. All right, so this is the problem that VALIFT was trying to solve. Okay, so I want to give you a couple more interesting results. So this tool can be used to improve compilers. Essentially, if you look at the source code, right, the left part is original source code, and the middle is the decompiler output produced by decompiler panoramics, and the right hand side is the result from leap mark. So you can see they're missing the red part of those things are missing the types. Okay, so with this VALIFT algorithm, we are able to recover those red part missing types. Okay, and this is another interesting application which I thought was very cool. So this is a real malicious, smart contract that was on the Ethereum, I think some of the popular blockchain, some time ago. So it was a hybrid kind of thing. So it has embedded inline assembly together with the source code. Okay. So the developer, those guys, basically they did a rug pull. They basically moved a lot of money away, and how they did was, they basically really hided the malicious behavior in that inline assembly. Okay, so when an auditor look at this in that inline assembly, if it does not know the type of the variable, it could be difficult for them to audit. Then we tried our tool on this piece of code. We realized, oh, what they did was really to turn a map. So the type of variable is a mapping corresponding to some address and tokens, essentially. And according to the standard of the ERC, some standard, if you want to transfer some money, you should emit some events, that can publicly available on the blockchain. But these guys did not. They tried to hide this behavior with building assembly to, escape from detection of this kind of behavior. Okay. So, anyways, we found, modified a variable of type mapping, which typically represent the balance of an address. So the code secretly stores a large amount of balance for that address. Okay. So it's illegal token insurance. Yeah. So, if you were seeing something like this, you would not interact with this contract, right? Would save your money. All right. So now I'm going to talk about the technical details. Right. There's a lot of details in the paper. I hope I can convey some high-level ideas here. So essentially, you have this bytecode, you have EVM, and then EVM execute the bytecode, one by one with different kind of operations, right? And there's a stack, there's a memory, and there's a storage. The storage is permanent, it's very expensive. So it's very difficult to really look at the code and find out which variable actually, hey, is this operation operating on a variable itself. So the first thing we did was to try to approximate, hey, this is a potential variable here, okay? So essentially the idea here is we look at the operations of each of the bytecode, look at the top of the stack, essentially say, hey, what this operation is going to do with this top of the stack thing. Maybe this is a variable, right? So this is the basic idea. We look at the top of the stack, we look at the potential operations, we find, oh, this is, m load, right? And then we know, oh, this is a potential variable. And if that's something else, this is not a variable, something like that. Of course, they're false positives, right? Maybe, the compiler can generate a lot of boilerplate, for example, memory address, indexing, those kind of things, and those are not variables in the code, okay? So we try to address those problems. Now we find, oh, the compiler typically does, that's something like this. Okay, so once we have approximation of such thing, then we try to identify its type one by one. There's a few interesting observations in the operations of the EVM. For example, permission check. Whenever you see, oh, there's permission check, then typically this is checking the address of something. Then you know the type of the variable is an address, right? And essentially the 3 steps we're doing, okay? Analysis, collect, and refine, okay? Let me show you how, this. For example, if you have a variable here and you see, oh, there's a push, then there's an equal, right? And it gives you the hints, this is a potential Boolean variable, right? And if you see, oh, there's a caller equal, and oh, this is a hint at an address variable, right? Some high-level hints you can have. But this is not perfect, right? It only solves 30% of the problems. We still need a lot of fuzzy type refinement, which is, to me, is pretty interesting. Okay, so what we realized that we can develop a type lattice for this problem, okay? So remember at the very beginning that all variable types are at the bytecode level is just 256 bits, right? So we try to map those bits into very low level at the leaf side, right? But there's an intermediate fuzzy types, okay? So we classify the type could be a value or could be a reference. Reference is kind of a data type with nested, types, right? You can define a high-level thing. And then at the lower level, it could be a value, could be a string, or could be a uint, unsigned int, right? And reference could be mapping, could be abstract with an array, things like that. Okay, then there's 3 steps of type refinement here. One, we assign a fuzzy type to a variable based on the access behavior. So the observation here is that despite all variables of the same 32-byte type in bytecode, they fall into 5 major categories according to how they are accessed. Let me show you here. These are the 5 major types here. Okay, some details. So when we look at the sequence of operations, we see, oh, actually, look at this, we can classify them. And then step 2 is we want to refine a fuzzy type, one of the 5 types, right? Based on some additional hints or to specific types. And here's an example, right? So if you see there is an AND, right, a variable with something, right, you can easily classify that as unsigned int. If you see that E0, which is an operand, in the bytecode, you see, oh, this is a bool, right? So by doing this, you can further refine it to some concrete types. And then there are still some remaining fuzzy types. So what we are going to do is we develop some more rules looking at more, operation subsequences. Okay, so overall, with all these rules together, we were able to recover like 99% something like that in the end. Okay, so this picture shows the overall picture of this. So there's 3 steps: type, lattice, refinement. Okay. Let me show you some results. So we evaluated on 35,000 real-world smart contracts. So this picture shows some high-level results here. We also compared with these decompilers. I know I'm running out of time. I want to just show you one more application here. This technique can be used to enhance smart contract fuzzing. The idea here is a lot of fuzzing approach based on identifying read and write dependencies. Okay, if we can tell the type of the variable, especially for those nested types, okay, we're able to precisely identify read and write dependencies on something. Okay, so we found this actually improves smart contract fuzzing by some significant percentile. Yeah, so that's the conclusion here. I can stop.
We have time for 1 or 2 quick questions.
Hi, thanks for the talk. I should probably read the paper, but could you also tell what are the main challenges in this? I mean, there have been a lot of prior work which have tried in inferring types from untyped code. So what are the main challenges here?
I think the challenge is, I mean, there's a lot of challenges, right? Previous work, the best work, proposed, on this topic, they can only recover 20% of the types precisely, right? The key challenge is the types are missing, right? You don't have those debugging information. You have to infer in a way. There's no formal rules for you to infer this is absolutely that. So there's a lot of fuzziness in the type, right? Oh, I see. What do you mean?
Tons of work, I mean, 30, 40 years ago, right? Which is trying to infer types. I'm just curious, what are the main challenges here?
Well, I mean, this is very, very domain specific, right? You're talking about blockchain and it's the things very domain specific. For example, those patterns, those rules, those operation sequences, you only see this kind of thing in Solidity.
Okay, in the interest of staying on schedule, let's thank Jeff again. I'm sure he's happy to answer more questions offline. So the last speaker of this session is going to be Mechana, and she's going to be talking about cool application or form of BDDs. With that, hopefully.
Yeah. Hi, everyone. My name is Meghna. I'm from UT Austin, and I work with Swaraj Chowdhury and Tom Reps. I'm going to talk about weighted context-free language ordered binary decision diagrams. So what is this decision diagrams? It's a hierarchical data structure that can represent enormous sets, vectors, or matrices very compactly. What do I mean by this? In the best case, an OFN data structure, size data structure, can represent a set with 2 power n elements efficiently. So that is, you get a double exponential compression using this. So traditionally, BDDs have been used to represent sets very efficiently. They give exponential compression in the best case. However, they're not hierarchical, and they do not have any weights. That is, they do not have weights across the structure. The value of the function is only at the leaves of the decision diagram. There's this another data structure called CFLO BDDs, which gives double exponential compression and is good for efficiently representing large sets. But what if you have this a function where you have large output value set? In that case, a unweighted structure does not really help, and a weighted structure where you have weights along the structure will really help, and this is work on weighted binary decision diagrams. I'll talk about this in the talk. we're going to talk about weighted CFL abilities, which achieves best of both the worlds. That is, it's good for representing large structures, and it's also good in case where you have large output set. So we use this to represent vectors and matrices, large vectors and matrices efficiently. And this was particularly useful in this case of quantum simulation, where we observed that it really gives best of both the worlds. On these quantum benchmarks, weighted CFL abilities perform as well as weighted abilities and CFL abilities. So we're going to talk about weighted abilities, then weighted CFL abilities, and then the application to quantum simulation. So let us take a look at this function of a Harman matrix. It's a matrix over 4 variables, x0 and x1, which represent the row variables, y0, y1 representing the column variables. The right-hand side shows the decision tree representation for this function. You have 4 variables. These are called plies, and you have decisions corresponding to it. The values of this function are at the terminal leaves. And at every decision node, you have a 0 decision or 1 decision, 0 corresponding to the left-hand side decision, and 1 to the right-hand side. Now, for one particular value of this function, the assignment would look like x0 equal to 1, y0 equal to 1, x1 equal to 1, and y0 equal to 0. You would traverse the path in this tree. You take the 1, 1, 1, 1, 0, and you end up with -1, which is the value of this function for this assignment. This is a decision tree. It's a standard decision tree. When you go to a weighted decision tree, notice that you still have this decision tree where you have 4 variables. But the leaves, the terminal leaves are always 1 and 0. They do not correspond with the values of the function. You have decisions as similar to what we have seen before, but along with decisions, along with decisions, you see the red highlighted numbers. They are the weights that correspond to the decisions that you're taking. And this will help you get the value of the function for that assignment. Let's see how that is done. For this assignment of 1, 1, 1, 0, you start with the function at the top of the tree. You take the corresponding decisions 1, 1, 1, and 0. But as you go along the tree, you compose the values, red highlighted values here. In this case, the composition is a multiplication operation. So you would do 1 into 1 into -1 into 1 into 1 into 1, and you end up with -1. And this is the value of this function for this assignment. So now that we are seeing weighted decision trees, if you notice, these purple highlighted subtrees are all similar, and they can be merged. You do not have to use different representations for the same thing. So you can restructure the edges to have one common subtree representation. You can do this at every level, and thereby you have a much more compressed representation. As you can notice, there's this decision nodes that point to the same next decision node, and you can remove them as well, and you have a weighted binary decision diagram representation. This is a very efficient representation. It's more compact than the decision tree representation. In the best case, you have an exponential compression, and you're also guaranteed canonicity. That is, for a given variable ordering, you have one unique representation of the function. This is helpful because you want to do efficient equality testing when you're actually testing between if two functions are equal or not. Either also computationally efficient, that is, the algorithms run in polynomial time in the size of the input weighted BDDs. These are some good properties about weighted BDDs. And we want to see how we can move from weighted BDDs to weighted CFL BDDs. So let's take this function again and the weighted BDD representation. Remember, we removed those 2 unnecessary nodes. Let's add them back. So you have this weighted BDD representation. Let's take a look at this x0 function. It's a split node. That is, you have 2 different nodes when you take 0 decision or 1 decision. Let's take this node and add a circle around it. These circles, we're going to call them groupings. Let's do this for y0, x1, and y1 again. And along with this, now we're going to add hierarchy. What do I mean? By this, you add another grouping. These are the level 0 nodes. These are the level 0 groupings. Add a level 1 grouping and extend these edges so that it still represents the same function. You're going to, again, traverse the path in the same way, but you're just adding some sort of hierarchy. Add this, add another level of hierarchy, and just extend the edges as shown here. Now, this is a uncompressed weighted CFL BDD. We'll see what's special about it. So if you take a look at this, the bottom half of the structure is similar to the top of the structure. And you can, as we have seen in case of moving from weighted decision trees to weighted BDs, we have compressed structures, right? We're going to reuse only one of these groupings, and we're going to restructure our edges. So let's remove this grouping. Let's restructure this edge to use only the first one. This way, you have a much more compressed representation. You have only, for one particular sub-function, you're using only one representation in memory. So these weighted CFLBDs are hierarchical weighted decision diagrams. They follow two principles. One is the matched path principle. If you notice here, you do not, though there are a lot of edges here, you do not run into cycles, because if you enter through a solid edge, you always leave through a solid edge. And if you enter this grouping through a dotted edge, you always leave through a dotted edge. This way, it follows this matched path principle, and you never run into cycles, and all the assignments are represented by the structure. It also follows this contextual interpretation principle. That is, if you notice, the decisions are always taken at the level 0 nodes. And there are weights corresponding to these edges. But these edges are not corresponding to any particular variable, as we have seen in case of weighted BDs. The variable that you're reading depends on the context when you're reading the assignment. And this way, you can actually reuse substructures without assigning any variables to it. So for this example of, as we have seen, 1, 1, 1, 0, which leads to -1, you start at the top grouping, take the path that follows, take the decision of 1, take the path, you end up with now y equal to 0, y equal to 1 decision, follow the path, and as just take the path from level 2 to level 1 to level 0 and then come back, and then you end up with at the terminal value. Now compose all the red highlighted values along this path, as we have done in case of weighted BDDs or weighted decision trees, and you'll end up with -1. So all the assignments are now encoded in the structure. So why is it called weighted context-free language binary decision diagrams? Because this follows a matched path grammar. It's a balanced parenthesis grammar where the edge has a weight. Though it's a regular grammar, because it has this balanced parenthesis, it's called context-free language binary decision diagrams. So when we are moving from weighted BDDs to weighted CFLBDs, we're adding hierarchy with this procedure call mechanism. What do I mean by procedure call mechanism? Let's consider this as a procedure, which is being called from two different call sites. And depending on the call site, you're returning to a different point in the original column. So this idea of procedure calls is giving you savings. And when you add this at every level, it gives savings on savings and on savings. And thereby, you have a much more compressed representation. So if you see the x0, y0 part of the weighted BDD is represented by this blue highlight structure through the solid purple edges. And the green structure corresponding to the x1, y1 is now represented by the same structure, but through the dotted edges. What is weighted CFLBD? It's a hierarchical structure. So at every level, you have groupings. At level 0, you have the decisions. As you can see, the fork node and a don't care node. And you have a weight associated to every decision that you take. And at every other level, you have your grouping is divided into two parts. One is the A connection and the B connections. It's a bit of terminology, but basically you're moving from level I to I-1 and returning from I-1 to I. And this way you're introducing hierarchy and thereby having compressing substructures. You add some more structure invariants to make it canonical to ensure that you have only one unique representation for a function. So weighted BDDs are read-once branching programs. Weighted CFLBDs are acyclic programs with non-recursive procedure calls. The key benefit is that weighted BDDs get their compression from sharing subtags. Weighted CFLBDs get their compression from sharing middle of a DAG. So in the best case, you have one grouping at every level, and 2 power 6 variable function is represented by 6 groupings only. So in the best case, you have a double exponential compression over decision tree, and a exponential compression of weighted BDDs. They're canonical, and they're also computationally efficient. So is there an exponential gap? Let's take a look at this function of a population function over n-bit variables set, it is 2 power the number of ones in a binary representation of x. So the left-hand side shows the weighted BDD representation for this function, where for every decision, you have 1 as the weight for the 0th decision and 2 as the weight for the 1 decision. As you can notice already that there's a lot of similarity. There's a lot of structure in the weighted BDD representation. And you can use hierarchy, as I've shown before, to end up with this weighted CFLO BDD representation for the same function. So if in this case there are 4 variables and you end up with 4 nodes in weighted BDD, and weighted CFLO BDD you end up with 3 levels. As the size increases, as n increases, you'll have 1 node for every decision in case of weighted BDD, so it would be a size O of n. In case of weighted CFLO BDD, it's O of log n. Thereby you have exponential compression with respect to weighted BDDs. What about CFLO BDDs? They're also hierarchical, but as we have discussed, they do not have weights along the structure. They only have weights at the leaves. And if you have this function, which has a range of n different values, so 2 power I to 2 power 2 power n, 2 power 0 to 2 power 2 power n, you have n output values, and therefore the size of structure is at least O of n. So you have weighted CFLO BDDs, which was O of log n, and so it's exponentially succinct than CFLO BDDs as well. So we have seen how weighted CFLO BDDs are better than weighted BDDs and CFLO BDDs. What about the algorithms that you run on weighted CFLO BDDs? How do you do those? So in a typical divide and conquer approach, which is used in weighted BDDs, you have 2 problems of half the size. But in case of weighted CFLO BDDs, you'll have gamma problems with half the number of variables, because you're dividing in the number of variables and not half the number of the output values. So at every connection, as I said, you had an A connection and B connection. For any algorithm that you want to design using weighted CFLO BDDs, you would first operate on the A connection groupings. You'll compute some symbolic information which will tell you what to do with the B connection groupings. And this way, you'll propagate this information. You'll also note that you'll have to use the weights at the decision 0 levels in some appropriate way according to the function that you want to represent. So if you want to do matrix multiplication, you'll compute one kind of symbolic execution. If you want to do a concatenation or a function addition operation, you'll use another kind of symbolic information. But you'll have to accumulate the weights and assign appropriately. So these are the, okay, so far we have seen what weighted CFLO BDDs are. Now we'll see what is its application. So weighted CFLO BDDs, they can scale to much larger problem sizes because of this compressed representation. There are also harder problems with large number of output values. However, they have some extra structural constraints that you have to add. As I was saying, you have to have the A connection, B connections, and appropriately have the edges. Along even the level 0 groupings have to appropriately be assigned the values so that you have a unique representation. But do we recoup these overheads? In case of quantum simulation, we see that we do. So if you take the number of qubits that you can scale to, we can see that weighted CFLO BDDs perform as well as CFLO BDDs and weighted BDDs for these set of benchmarks. If you want to look at the performance specifically for this, let's say this benchmark of GSZ, if you take a look at the dark blue line, the dark green line, weighted CFLO BDDs perform as well as CFLO BDDs, and they perform much better than weighted BDDs in this case, in terms of both time and memory. For another function of GSZ, they perform better than CFLO BDDs and weighted BDDs. We notice that in case of QFT, where the output value structure has a lot of values, you notice that weighted CFLO BDDs perform much better than CFLO BDDs, and they perform as well as weighted BDDs, though in some cases, the number of nodes are slightly different. So I also note that this is all on log scale. So to conclude, weighted CFLO BDDs give exponential compression over weighted BDDs and CFLO BDDs, where weighted BDDs get their compression from sharing DAGs, sub-DAGs. You get weighted CFLO BDDs get the compression from sharing middle of a DAG, and adding this extra weights to the structure gives you ability to scale to problems where you have large output size. And we see this in case of quantum simulation, where you're able to scale to much larger number of qubits. Thank you.
thank you for the nice talk and the nice diagrams. So I was wondering, so besides quantum simulation, have you tried like other applications of this variant of BDDs, like say in like model checking or something?
Yes. So we did try them. In some cases they do scale, but in some cases they don't, and that is because of this extra structure that this hierarchy is introducing. So one idea is, as you can see, there is this level I goes to I-1 at A connection, B connection. Maybe you can relax that grammar balance parenthesis grammar, and this slightly different grammar will help you scale better. And I think that is what we are focusing on right now in the future steps. So we did try, they did not scale on many of the benchmarks as well as the scale in case of quantum simulation, but we hope that our next work can help us scale those cases.
There are some programs here where you get like much better compression.
Sorry. Yeah.
Oh, sorry. So there are some like circuits where you get much better compression than other ones. Is there like some intuition for what kind of structure is in the circuit that gives you better compression? Or
yes. So there. Okay. With respect to weighted BDDs, you get for these structures you have much better compression. That's because in many of these algorithms, you have, let's say you have n qubits, and you apply something like a Hadamard gate over all the n qubits. If in those cases, this hierarchy helps, because you already have a nice structure, this hierarchy helps you give much more compression of the substructures, which is not possible otherwise. So that's why it scales to much better numbers in case of this. In case of QFT, it scales better than CFLO BDDs by 128x. That's because you have a large number of output values in QFT. And this weights across along the structure is helping you give that compression. Yeah.
Yeah. Thanks for the inspiring talk. So something critical for BDDs is the ordering of variables.
Yeah.
So I guess it's still critical for your approach.
Yes.
But isn't there a new dimension of problem how to split this into the several dimensions? So I'm not sure whether dimension was the right term, but you have certain partition, right? Doesn't this complicate the process of finding a good variable order?
So we've used one variable ordering. We mainly dealt with matrices. So an interleaved variable ordering of row and column variables was the ordering that we used. So when there are two parameters here, 2 degrees of freedom, if you say. One is the variable ordering. The other is the grammar. In this case, the grammar is fixed. That is, at every level, L, you always divide it by half the variables. So L minus 1. So first half variables go to the first A connection, L minus 1. The second half of the variables go to the B connection, another L minus 1 groupings. So the variable ordering is similar. The variable ordering problem is similar to that of BDDs. But if you want to, as I was mentioning, if you want to relax the structure a bit and want to introduce a different kind of ordering where you have 3 sections saying 1/3 of the variables, 1/3 of the variables, and 1/3 of the variables, that introduces another level of challenge. I think that's something to explore that I think hopefully we'll do it.
Thank you.
Yeah. Thank you.
Thanks for all those great questions, everyone. Great session.
Your slides are.
They will be
okay.
there.
Okay. All right. So it's 4 o'clock. So since formal methods 1 is not enough, we're here for formal methods 2. So please take away, Amanda Sharda.
Yes, thank you. We've had 1 formal methods, yes, but what about 2nd formal methods? I'm going to present my joint work with Philipp Rimmer on accelerating counting constraints on string solvers. And I promise I will make that sentence make sense to you once we're finished. So string constraints these days are everywhere. They're usually in input validation. You might want something like find me a string that passes this validation regex, but you also want it to contain a naughty script tag. And then, worst of all things, you might also have length constraints. And once you start having length constraints, that's when the bad things start. So I assume that we're starting with a bunch of string constraints that we're handing off to a string constraint solver for solving. This is an SMT solver. And we imagine that we have a bunch of these kinds of regular language memberships. You will realize at the end of this example that it's calibrated to be a great example, which is why the automata don't make sense. But we also have a substring constraint that says that string number 1, in addition to matching some regular language, has to be a substring of string number 2, starting at index I and having length n. And that's what I've been trying to visualize in this block diagram there. We also have a bunch of constraints on those indices that require that we have something before and after the substring. So this is essentially to make the case a bit interesting. The first 2 constraints can be easily handled by a regular language constraint. So that's not super complicated. It's just automata theory. Standard undergraduate automata theory is enough for that. The substring constraint is a bit more tricky. So if we assume that we have an automata-based string solver, we can take this automaton and then we can turn it into a substring accepting automaton by adding an extra transition at the beginning and the end that will accumulate the prefix and the postfix, and they will just do this for any transition. Now the problem becomes, how do we handle the counting? Usually we do this by turning this common normal automata into a parec automata and having it increment some register. So in this case, we increment the prefix register I when we take the first transition. And we do the same thing for n. So now we know how long the prefix string was. We know how long the content string that we're matching is. And I'm also adding a length constraint that will come in handy later. So I also count the length of the entire thing that's accepted. And that handles the substring constraint. If we use standard methods and blast this into some form of linear equations, we also get the inequalities handled for free by our SMT solver, and now we just need to count the length of the other string. We do that in the exact same way, so we just add 1 register that counts the length. Now we've translated this problem that is about a bunch of annoying and complicated functions into finding the intersection of these 2 automata, both that have some registers, translating them into a set of constraints and then solving them. So the problem that we handle more generally is that we have some number of products of automata. We count something using some kind of homomorphism that does some counting. I'm being hand-wavy here, which is why I'm waving my hands. And then we have a bunch of integer constraints on the final values of those counters. So this is pretty much an intersection problem for parec automata if you like complicated language. So this will look like this. You have a product that you want to compute, and the previous state-of-the-art method is to take this, run it through a bunch of encodings, get a bunch of these nice formulas on the right. But the problem is that in order to do this, you first need to compute the product of the automata and then do the translation. When you do that, you have exponential blow-up. That's bad. This is a real automata, but it's not this one. A second problem that you also get is that some of these constraints have a complicated Boolean substructure that comes from the fact that you need to enforce connectivity in the presence of loops. So if this transition is used at any point, you need to make sure that we're coming in through one of these, and that generates a lot of OR clauses, and those are usually expensive to handle. So the key ideas that we present in this work is a method for pruning automata terms using the underlying solver before we compute the product, so that the product is smaller. We also delay the enforcement of the expensive connectivity constraint using standard online methods, more or less. This allows us to make sure that the product is as small as possible, and we also have a splitting strategy to allow us to whittle down the automata even more before we compute them. We put this in a box that we call Catra. That's the thing we produced. Catra consists of the method itself that we call PC star. This is the thing that you can generalize and use in other products. It talks to an SMT solver, in our case the Princess SMT solver, and it Princess handles linear constraints for us. And that is the artifact that we submitted as well. So this is sort of the output more concretely. This is meant to be used by an SMT string solver. So the string solver asks this entire thing to handle a bunch of constraints that happens during string solving, and then it gets back answers of whether they're satisfiable or not. But you can also hook it in various places. So we return to the example, and I will be working through this example to show you how it works in practice. So I start by adding that both automata has to accept a string of the same length. That's why I added the length counting constraint to the bottom automata before. That will allow us to do some more pruning. This is implied, but I do it anyway. Then we need a way to go from transitions to the register constraints that we already have. So we know things about the register values, but we don't know anything about the transitions of the automata, and those are the ones we want to prune. We do that by giving each transition its own fresh variable that doesn't occur anywhere else. And they also are only given one constraint, and that's that they have to be more than 0 or 0 or more. And they represent how many times that transition is used in a solution. We can then tie those to the register values by just adding a constraint that the number of times or the value of each register is the sum of its transitions. So for example, this variable here is exactly identical to I because the register I appears in exactly one transition, and it's that one. The same thing happens for the lengths, and the same thing happens for n. So these transitions sum up to become the final value of the n register. So now we have, whenever we have a constraint talking about one of the registers or the final values of the registers, we can now translate that to say something about the transitions. We also have a bunch of constraints that come from the fact that this is an automata. For example, if we go into a state, we need to come out of that state the same number of times. So that means that the sum of the incoming variables is equal to the sum of the outgoing variables, except for the initial state, which has an initial flow of 1, because we stop the automata once. So this allows us to do some reduction in variables, because whenever we have something like this, where we come in exactly as many times as we go out, we can already remove some variables from this and using just standard equality propagation. Now it's time to start pruning the automata. And we can do that by performing linear equation solving on the equations we already have, so that in this case you can see that the values are now distributed across these sums, so that we have this. And this allows us to conclude that n has to be 2, because 2 minus n has to be greater than 0. Which gives us both an upper and a lower bound on n, and there's only one integer that fits in there, so we know that. This gives us an automata where this transition is used 0 times. That means we can remove it entirely. And these two become 1. By similar reasoning on the bounds of I also becomes 1. So now we have an automata where we know exactly how many times we take these transitions. And we also know, crucially, that we don't take one of the transitions. So now we have just a stick down there. That's a much nicer product. But we still have some more decisions that we can make. And this is mainly to illustrate. Under normal circumstances, I would compute this product straight up, because it's very small. But we can still get it even smaller if we want to. And you can see here that we have 2 choices in the upper automata of where to go. Either we go through this strong connected component at the top, or we go in through the one at the bottom. We can pick exactly one. So now we can generate a case split for the underlying SMT solver, where we say that, okay, we pick this transition, it seems interesting, we try to isolate that one and split that into two cases. One where we don't use that transition, and one where we must use that transition. And then we hand that off. And now we get a smaller automata. So we start with the equals 0 case. And when we've done that, we can start thinking about the connectivity constraints. So now we have a much smaller automaton. We know that we're not taking the upper path. That one is no longer reachable. But we also know that this loop has something that could potentially not be 0. But that can't be, because there's no way to that state. So we add a blocking clause that says if B6 there is 0, the incoming transition, then that implies that the loop can't be used. And this will further reduce the possible things. So now it's time to compute the product. We just have these two sticks, and we can just smash them together. But you will realize very quickly that there are no overlapping outgoing transitions from the initial state. So modulo dead states, this product is empty. So we've now completely removed this case, and we would have to try the other case in the case split, and that one would have the same result, because this example is unsatisfiable, but it's not trivially unsatisfiable. So the outcome of this are these results. What you see here is simply us. So we took a bunch of inputs of this type of problem, that comes from Ostrich doing trying to solve the PyX benchmark suite, which is a standard string constraint benchmark suite. And we have implemented a bunch of different backends that solve the same problems. So to the left, you can see how many solutions we managed to compute within a 30-second time budget. And to the right, you can see how long it actually took the various backends. And the alternative we have is us, which is PC star. In the middle, we have the previous standard approach, where we essentially just translate compute the product, translate them into using standard methods, and hand them off to the same underlying solver. And to the right, we have the new XMV model checker. And as you can see, we do slightly better than new XMV, and a lot better than the previous baseline approach on, in particular, unsatisfiable instances. That shouldn't be super surprising to you, given that unsatisfiability is easier to detect in this case. If you have a satisfiable instance, you have to compute the entire product, and that's always a bit more expensive. But from the box plot to the right, you can also see that we generally come back with solutions faster, and that's very important because we are at a leaf in a rather complicated stack of various things calling each other. So in summary, I have presented a method for computing some projection on pairing images of languages or their intersection. I have shown how we can lazily materialize the products, and I have shown how we can lazily enforce their connectivity constraints instead of upfront having to encode them. And I've also showed very briefly how we can do case splitting to drive those. Thank you.
All right. Thank you. So we got some time for questions. All right, let me warm up the audience. So I think, so it seems like your technique does depend on like picking the right edge to cut in order to get those smaller products. Can you comment a little bit about like how well that works, how predictable that is, that sort of thing?
Yeah, so of course we tried different strategies. And essentially, so all of these rely on finding strongly connected components and then computing min cuts across them. And generally what you want to do is you want to cut as early as possible in the automata, because that makes sure that you cut away as many transitions as possible. It also helps to try to cut big components when you're trying to isolate them from the initial state. So in general, that's the strategy I went with. I tried a bunch of other things, but that's the one that works the best.
Could any of the techniques that you have invented be backported into the things that you're comparing with? Like your baseline and your...
For NewXMV, I don't know, because I have no idea how NewXMV works. I assume that it does things that are similar, because it has also has pretty good performance, and it can't possibly be computing products up front. That would just explode. So it has to do something similar, but I'm not well versed in model checking, so I don't know how that usually works. The other method is about as good as you can make it. Going into the exact details of how we implemented the baseline approach is far outside the scope of this, because it would take too long, but it essentially can't be improved further. So no, not that I know of.
So I have a very simple question. You mentioned Ostrix as an SMT solver that you use, right? So did you try other SMT solvers in combination with your approach?
So the problem is that what we need is, so the usual question that comes up is, why aren't you doing this with Z3, for example? And Z3 is word equation based, which means that you can't easily do the translation. It has completely different problems, simply. There aren't that many automata-based string solvers. I think Chow is the other one we have. The easy answer is that the integration is not super straightforward, and usually they make other trade-offs. So Chow, for example, only accepts strings that would lead to automata that don't have the problem of loops, for example.
So it wouldn't scale simply, or you couldn't?
It could be implemented, but this is pretty much the string solver that does this. It's also the one that's best in its track on SMT comp, which is why it's interesting to try to improve it. That's a separate result that's also in the paper. So we actually take that, the fragment that it does really well, and we make it slightly better at that one.
Okay, thank you.
I should have run out of time.
Thanks. Right. I can speak really slowly if you like. No.
Do a James Noble and start asking the question in French.
Yeah. Sure. No. So like, which one of the discrete techniques that you invented in order to get to this result, like, is the most influential? Like, which is the most powerful one, and which is the most surprising to you?
The most powerful one is the delayed product computation, because it's essentially what happens in the baseline approach is that it spends all its time doing product computation. And in fact, most of the products don't even fit in RAM, regardless of how much RAM you give them. So that's by far the most impactful one. And that's also why we started introducing case splitting, because it turns out that just doing the pruning before you compute the product will not give you enough bang. You need to further whittle down the automata so that they're small enough that you can compute the products. So I think that's the one that really gives some bang. The splitting strategy isn't hugely important. It does some marginal improvements, but really just doing it at all is what matters. There's also some trickery behind choosing which products to compute. Okay, I'm being waved off stage.
So Fernanda again. All right. So our next talk is by Yao Zhusun from University of Hong Kong. So take it away.
Yeah. Thank you everyone for coming. First let me adjust the microphone a bit. Oh, that's okay. Yeah. Welcome to my talk. Today I want to talk about imperative computational programming. And this is a joint work with Wenjia and Bruno. first, you may notice this. We have a very long subtitle, and I want to divide it into several keywords. Yeah. Then we start with imperative computational programming, ICP for short. And computational programming is a programming paradigm we recently proposed to mainly solve the expression problem. If you know expression problem, if you don't know, that does not matter, because it's basically a dilemma of extending two dimensions. One is the expression, one is the operations over these expressions. For example, if we want to model a mini language, for example, we have variables, assignments, sequential composition, then we go for the x-axis, and we want to extend more, like we want while loop and do while loops as two variants. And also, on this axis, we want to extend, we want to implement more operations on these data types, like we want to print, we want to construct a control flow graph on it. In CP, conversational programming, we have a very modular solution to it, and we can have 4 modular traits that each implements every point of in this coordination system. And if we take a closer look at, I want to mention that we also support modular dependencies, like we can depend on print on the red top corner, that our graph, the new node function, also have a self.print to have the modular dependencies. In some similar approaches like final tagless, it's very difficult to implement that. But we want to have a closer look at this function because we have imperative things like references. For example, the goal is to build a control flow graph like this one. And sorry, I pressed the wrong button. And this one has a data type graph that's a point, like the pair of nodes, pair of references of nodes, like 2 pointers. One points to source, one points to sync node. And we have made a lot of use of references like assignments, creation of references, and dereferences here. The ban is for dereferences. The adjacency array is like a mutable field here. And here comes the intersection types. To make use of the modular traits, we may want to merge them together. Like here in the merged, we have all the constructors. Then we can build a expression making use all of these constructors, and every constructor have print and graph together. The operations can be used from this merged. And here the comma is a merge operator, and is virtualized below. And on the type system, on the type level, we have intersection types serving as the interface here. And you may wonder, what's the problem with intersections here if we want to add in multiple references? Now we dive into the type theory below our imperative computational programming. Here, an intersection type basically means if your expression E has type A, and E also has type B, then E has an intersection type of A and B. That's a basic idea. And simple example is positive numbers and natural numbers. You can find there is a subtyping relation between them, and you can easily derive that 1 is both a natural number and a positive number, so it has type net and post. That's a typical introduction rule for typing. And for subtyping, we have 3 rules. The first 2 handles the case that intersection types occur on the left-hand side. For example, if you have an expression E has an intersection type, you can use it as if it just has net or has pose. The third rule, you can use it to permute the components inside the intersection type. For example, net and pose is equivalent to pose and net. That's very intuitive. You can derive it using both all the three rules. And for references, we have three primitive operations. The first one is to create a reference. The second one is to do assignments, and the empty parenthesis is the unit type. It means you can discard it. And the third one is the dereferences. To give you an impression on these type systems, I have a program that creates ref1 to have a reference cell that stores that 1, and we assign 0 into it. And at last, we want to dereference it and want to use it as a positive number. You may have noticed it's wrong. And let's see how can our type system detect it. Here, you can find ref1 definitely have ref pose, but for assignments, you cannot use ref pose as ref net because the subtyping for references is invariant. So, yeah, on the second line, there should be a type error. And when intersection type comes, the programs becomes a bit complicated, and we can bypass the type checking to make it type unsound. Again, let's go through it from the first hand. So from the first line, we have the reference type. We can type ref1 with the reference type refnet and refpose. This intersection type with both reference types, and initially x points to 1. So far, so good. But if you want to do assignments, you find it works because you can take the left half of that intersection type here, and you can assign 0 into that reference cell. And oops, at the last line, you want to use 0 as a positive number, but it's not. So you may encounter a runtime error. In other words, it's type unsound. Actually, it's a well-known problem, and the solution is proposed by Davis and Fanning that they impose a value restriction. If you are familiar with OCaml, you may have seen a similar version of that value restriction, but this time is to make sure that the reference does not introduce type unsoundness. Here, we can see ref1 is not a value, so you cannot type a non-value with intersection type here. So it's forbidden. Now the system back to type sound, but distributive type subtyping breaks type soundness again. Here, we have instantly invoked function, and with very long derivation. Trust me, that if you don't trust me, you can work it out, and you bypass the type, the value restriction, and get this expression with the intersection type again, and is back to type unsound. So that's a very complicated problem in the literature, and we don't find a very good solution in the literature. So how do we handle that? The bidirectional typing come to rescue. And before we have the comma in the judgment, it's called type assignment system. And it can actually be divided to 2 separate judgments, and this system become more algorithmic because for type inference, it has algorithmic meaning that E can be inferred to type A. And for type checking, you have two known things. One is expression, one is the type, and you checked the expression against the type. Usually, we also have a subsumption rule that to bridge, to fill the bridge between the two typing modes. Back to the very simple example on numbers, we can see that now one is supposed to infer typos, and that is the most precise type of one. And in most bidirectional typing systems, one expression can only infer one type, because that's a more deterministic way to do that. And if you want net, then you can check net against, you can check one against type net, and the subsumption rule will help you do that. In short, one can be inferred to be typos and also checked against that, but net can only be checked against net, but not to inferred to have type net. And here, if we want to apply bidirectional typing to references, Davis and Fanning propose a solution, but does not work as we already mentioned, because this system is almost equivalent to their type assignment system. We have a different formalization using bidirectional typing on the third line. And maybe to your surprise, the most important rule is the reference rule, the tref. And the difference is that we don't check, we use the inference mode here. And you can ignore the other two rules here and only focus on tref. You can see ref1 can still be, we can still infer ref1 to have type refpos and also check it against refpos. But now it cannot be inferred to be type refnet, nor it can be checked against that type. This solution is very simple, but it can solve the previous type assigned case here, because no matter the reference one or the instantly invoked function, they cannot have type refnet, because to be honest, we have the most precise type for all references, so that less precise type cannot be used here. So the type soundness is back again. You may wonder, if you want to have refnet, how can we do it? That's very easy. We can have a type annotation, and in a bidirectional typing system, it will invoke the checking mode, and you can naturally have refn, colon refnet, and use it as refnet below. But it cannot have refpos anymore. Otherwise, the type assigners will come back again. To conclude, our advantages over Davis and Fanning solution is, first, our intersection introduction is standard. We don't have value restriction. And distributive subtyping is supported. Why distributivity matters? Because we have shown in the very beginning. But first, logical implication is left distributive over conjunction. So that's a direct corresponding between the logical system and our lambda calculus. And more importantly, distributivity of trace is encoded as functions of records. And it enables nested trait conversation we showed before, and that's the solution to the expression problem. We cannot drop distributivity here for our ICP. Last thing, we have more in our paper, more introduction, complete code, and we have Coq formalization for both calculi. One is based on the calculi by Davis and Fanning, but employing our solution based on bidirectional typing. And a more complicated calculus is the foundation for our imperative computational programming, and both proofs are mechanized using clock. Oh, sorry. That's all for my talk. Feel free to ask me questions. And also, my co-author Wenjia is here. Yeah. Thank you very much.
Thank you. Questions? All right. So, I mean, it seems like a really simple innovation in design, and so I think that's really cool. So, can you say a little bit about how you end up with it, and maybe why it wasn't sort of in the original, if you will?
Yeah. Actually, we don't start with the problem found by Davis and Fanning. Actually, we start with. Let me just hold the microphone. You want to? I will step in first. And we actually start with our design of computational programming, and it's quite natural that we just. Since computational programming also use bidirectional typing for other reasons. For example, we have imperative, imperative polymorphism, and we have more complicated systems. We naturally have bidirectional typing, and we find infer can conclude a type sound calculus, and we find it's a long-standing problem in the literature. So we start from our own language and go back to the old problem and solve it altogether. That's the story of our design. Maybe you can add more things.
Yeah, it's some kind like that. At first we are not aiming to solve this question. It's like we solve it accidentally. Yeah. Yes. So at first we are going to like add multiple references to our own language in our group called CP. Yeah, you can use that language as well. So and when we add the multiple references and we see that their intersection type and multiple references and their findings work, and we see that their restriction is quite like to overhead. So we think another approach and accidentally it solved the problem in their paper as well. Yeah.
Very cool. Other questions? All right, I'll continue then. I mean, it seems like such a simple solution. So is it actually more expressive? Do you lose something? Is there a trade-off in the using the value restriction versus your system, or is it just better?
I think the most important thing is that one expression can only has one type. It's not true in some more complicated typing system that you may do backtracking. You may want to have, expression have multiple types, and only one of them works in the later stages, and you want to backtrack and do a lot of things. That's the case in another work in our group for type inference. Yeah, I think that's the most important restriction we have.
So one more.
Did you also compare or consider versions of the reference type which has two type parameters, where it is covariant in one parameter and contravariant in the other?
Yeah, you can.
For references, we are also invariant. Yeah, we haven't considered the covariant. Yeah. So now, for reference type, they are invariant. So maybe this is also one future direction that you can explore something. As I know, there's something like thick type, and also I'm not sure, but they can make it covariant. Yeah, I think that can be one future direction. Yeah.
Okay, let's thank the speaker.
Thank you.
All right. That's it. All right, so our next talk is going to be by Jonathan Costello from UC Santa Cruz. So take it away.
Thank you. I want to make sure I talk into the mic as I've been directed. Hi, everyone. Thanks for coming to our talk. My name is Jonathan. That is a very old picture of me. And today I'll be telling you a bit about our work on inductive diagrams for causal reasoning. This is work that I've done with my collaborators Patrick and my advisor Lindsay. So we've been using diagrams like these, known as space-time diagrams, sequencing diagrams, Lampert diagrams, and many other names, since at least the 1970s in an attempt to wrap our heads around how concurrent and distributed systems work. These diagrams visually depict the events of interest in a system. Often things like when and where a message is sent or received, but not always, and the causal relationships between these events across space and time. The way that these diagrams visualize causality as so intuitively is so useful that we see these diagrams at all levels of academia and industry. And I'm very much wishing I had larger font size. However, they are just pictures, not formal objects. In the worst case, you can barely manipulate them with a whiteboard eraser, much less with math. To reason formally about causality, we need a formal model of causality. Lampert's own 1978 model goes roughly like this. First, we have a collection of processes, modeling a fixed set of locations in the system. Next, each process has a sequence consisting of the events that occur on it. And last, we identify the pairs of events that comprise messages, where information propagates from one location to another. This traditional model has been enormously successful, and deservedly so, but it does have some potential pitfalls. First, it doesn't prevent you from representing something physically impossible, like a causal loop. You need to check or assume that your data is self-consistent. The structure of your data doesn't really help you in this situation. Second, it doesn't prevent you from representing inconsistent cuts. A consistent cut is something like this, where you separate the events of an execution into a clear past on the left and future on the right. If an event is on the past side of a cut, then everything causally before it also needs to be on the past side of the cut. An inconsistent cut, like this one here, fails to have that property. But again, the traditional model doesn't help us avoid inconsistent cuts. There's no connection between the processes that we're splitting and the messages that we need to respect. To play off an old chestnut, these illegal states are all too representable. Such problems are only exacerbated today at a time when more and more of our proofs are being mechanized in proof assistants like ROC or AGDA. These tools provide first-class support for defining data inductively and analyzing that data recursively. In an ideal world, we would also be able to analyze causal data this way, and without having to worry about whether the cuts we split our data on might be inconsistent. We should have a model that makes impossible executions unrepresentable, and use that causal structure to give us powerful causality-respecting tools of analysis. Well, that's exactly what we hope to have achieved with our work on an alternative formal model, causal separation diagrams. CSDs are causal by construction, avoiding the causal loops and inconsistent cuts we just saw. CSDs are defined inductively to support clean proofs that decompose into smaller pieces that are easier to comprehend and digest. CSDs provide a formal graphical syntax for causal data, as opposed to a set theoretic description with multiple moving parts. And CSDs can be given semantic interpretations into any desired domain of analysis. Syntax and semantics are, in my opinion, the crown jewels of programming language theory, so I'm super excited to be able to apply them to causality. Our paper not only goes into the theoretical aspects of how CSDs are defined, but also demonstrates their use in a study of logical clocks. With a trio of 3 closely related semantic interpretations, we're able to give the first generic proof of the defining property of clocks, the so-called clock condition, for a large class of logical clocks. As a side effect, we have what seems to be the first mechanized proof of the clock condition for 2 well-known matrix clocks. All of our results are mechanized in Agda. You can find our source code at this GitHub repository, but you can also find it linked from the paper. You don't have to worry about copying that down immediately. We won't have time to cover everything in the paper, so in the rest of the talk, I want to walk you through our key departure from the traditional formal model. With one small change in perspective, I hope for you to come away with a fresh way to look at causality. Let's return to the example diagram from earlier, along with its traditional representation. These 2 representations describe the same system execution, but they do so in very different ways. The labels are the only things directly relating one to the other, and if we remove those, these still describe the same state of affairs, but now you really have to cross-check the 2 representations to convince yourself of that fact. On the other hand, all of the structure is still there. The traditional data makes the structure of the diagram very explicit, while the diagram itself leaves it implicit. Let's start by making that structure more explicit in the diagram. The traditional data's top-level structure is the collection of processes, so the first thing we should do is visually separate those processes. Next, each of the individual processes has a sequence of events. We can visualize those sequences in the same way. Unfortunately, we can't really do the same thing with messages. That's almost by design. We made the order of events within a process our top priority, and messages are a fundamentally different kind of entity. Notice, though, that these messages always seem to cross the red dotted spatial boundaries, which run vertically, which run horizontally, rather than the blue dotted dashed causal boundaries, which run vertically. Just rotate the diagram on its side. The process local edges that cross the dashed causal boundaries are inherently causally ordered, while the edges that cross the dotted spatial boundaries between processes are not. We can also visually see how the consistent cuts of the diagram are split into segments. We have to pick one segment from each row, and link them together along the spatial boundary. Again, the fact that messages leak across these spatial boundaries is what makes it possible to accidentally construct an inconsistent cut. We argue that this bad behavior arises because we prioritize the spatial boundaries between processes over the causal boundaries between events. What happens if we transpose the order of decomposition? If we lay down causal boundaries before spatial ones? First, we'll lay down enough consistent cuts to separate every event. Next, we'll put spatial boundaries between each distinct location. We end up with a very different, if subtly so, decomposition of our diagram. Where the original decomposition depicted a structure consisting of 3 separated sequences of events, our new decomposition suggests a single sequence, not of events, but of global steps. In turn, these global steps give an atomic local step to every location in the system. In this diagram, for instance, there are 4 global steps arranged from left to right, separated by blue dashed lines. And each global step happens to contain 3 local steps, delimited by red dotted lines. This choice to prioritize causal boundaries over spatial boundaries is the fundamental difference between CSDs and the traditional model. Everything else is just a consequence. Something else that might jump out at you is that some of the local steps don't contain an event at all. Of course, that's because our processes observed different numbers of events. If you separate all of the events on one process, you'll cause the events of another to appear more spread out. But here's what I think is most interesting. Both messages and processes evolve over causal boundaries. Information never propagates directly across a spatial boundary. As an immediate consequence, a diagram that can be decomposed this way necessarily has no causal loops. If it did, we wouldn't have been able to call that loop, to cut that loop with a consistent cut. In other words, if we can construct diagrams this way, then they will necessarily be causal by construction. So that's point 1 from our list. What about points 2 and 3, where we talk about an inductively defined graphical syntax? Well, here are all of the local steps that we can build diagrams from. The first 2 should look familiar. A tick is just a local event on a process, and a no-op is the absence of such an event. The last 2, swap and assoc, don't model any actual events. Instead, they just allow us to rearrange the lines through a diagram. In particular, this allows processes that aren't immediately adjacent to talk to each other. You can think of these as structural rules in the sense from formal logic. The middle 2, fork and join, model the 2 halves of a traditional message. However, with a traditional message, both the process and message state come out the right-hand side or left-hand side, rather than diverting the message out the top or bottom. Yes. Unlike a traditional message. In fact, our model doesn't distinguish process state from message state at all. Nothing prevents a, quote, process from joining state with another process or a local event from occurring on a message. As a result, we refer to these inputs and outputs uniformly as sites, as in places where state can exist. In principle, this uniformity allows us to model other communication patterns, such as local processes that fork children, and even rendezvous communication, where 2 processes join briefly and then separate again. And we can still model the same unicast systems anyway. Now, graphically speaking, you can stick these tiles together however you like, as long as you line the wires up, and still get a consistent CSD. But under the hood, we've also mechanized a typed algebraic syntax for use in AGDA. The types here model not only the number of inputs and outputs to each tile, but also the type of state they carry in particular. In particular, we think of fork and join as taking a product of state, say the process's own local state together with a prepared message, and splitting them into separate locations on the network so that they can propagate independently. Finally, these are the combinators for composing local steps into global steps and for chaining global steps together into a full execution. At the term level, we use 2 separate types to strictly nest concurrent composition under sequential composition. For instance, in the type of concurrent composition on the left, the lollipop arrow is the name of the type of global steps, while in the type of sequential composition on the right, the double arrow is the type of CSDs writ large. However, this distinction is mainly for ease of induction. You can freely compose CSDs sequentially and concurrently. They'll just compute down to this representation. To cap this section off, let's return one last time to our example diagram. Here's the traditional data for this diagram, and here's the corresponding CSD in both graphical and algebraic syntax. We can see how for every local step, there's a leaf-level term in the corresponding expression, and for every cut in the decomposition, there's a composition operator. All of the state of a CSD is packed into this single object, and it's all ready to be given semantics like any other programming language syntax. We don't have time to get deep into the semantics of CSDs, but now that we've seen their syntax, I do want to give you an idea of what to expect from the paper. We defined 3 different but related interpretations of CSDs. The first is a proof-relevant analog of the classic happens before relation. Instead of simply saying that 2 events are or are not causally related, we interpret a CSD into a dependent type of causal paths through the diagram. These paths give concrete evidence of a causal relationship between 2 events, and they can be used directly to drive an inductive proof. The second is an interpretation into clock functions, assigning to each event its corresponding logical timestamp. The interpretation is parametric in a choice of clock implementation, so you can easily instantiate the same machinery over many logical clocks. In fact, we've just done just that for the Lampert clock, the vector clock, and 2 separate flavors of matrix clock. The third interpretation is into proofs of the clock condition, which relate the previous 2. The clock condition states that a clock is a monotone function from the causal order of events to the natural order of on the clock's domain of timestamps. Because we constructed these orders by parallel interpretation, we're able to give a completely compositional proof of this property, given only proof that a clock is locally increasing at every event. To close out, I would give my thoughts on where to go next, but you can talk to me after the talk, I think. The two highlights are, there's a lot of really interesting categorical structure happening under there that I'm really eager to explore. Symmetric monodal categories being the big old buzzword there. You see those all over concurrency. And also separation logic, weirdly enough. Yeah, come talk to me. That's all I have. Thank you for your time.
Some time for questions? Thanks for the cool Manum slides. Yeah. Which came first, the diagram or the formal model?
Oh, in our work or in general? In our work. That's a wonderful question. I think the impetus came from the use of formal models in existing work, where when you're trying to analyze things like, in our case, causal broadcast systems, and in a lot of other cases, you need some model of an execution and all the events in it in order to found your analysis against. Our experience, and from looking around at other people's work, is that building that execution is not only quite ad hoc, it's also quite a lot of work. And depending on which model you build from, it can easily dwarf in some ways, well, it can be a sizable fraction of the overall analysis. Our goal was very much to find another formal model that retained the same intuitive aspects as diagrams, but also had really nice inductive properties, so we could better factor our proofs and just make that much less of a headache. I hope that answers your question.
So Lamport's paper has, of course, the Lamport clock, but also he has some theorems about physical clocks. Can your work handle the physical clocks as well?
It's a good question. The short answer is no. We're focusing strictly on causality, and I think Lamport actually gives, in his infamous paper, an example of precisely how physical time and causal time do not exactly line up with each other. So I would say no, and it's not necessarily meant to do that, but I can imagine ways to take this further and try to incorporate some aspects of physical time. Nothing worth talking about completely, oh wow, rainbows in the sky kind of things, but short answer, no. Long-term answer, maybe.
My friends in physics have told me that space and time are the same thing, but you were able to get a lot of benefit by kind of swapping the two. What should I tell my physics friends? Why is this the case that you're able to get benefits?
So, to repeat your question, please correct me. You're asking if we can swap space and time and get concrete benefits.
I guess I'm just like, I've been told that space and time are like the same thing, but clearly there's something fundamentally different when you're able to get different compositionality through kind of putting
Right.
as the primary.
Yes. Yeah, so that's a good question then. Well, not then. I understand it. I understood it now. I think that the upshot is your friends are kind of wrong. The signature of space-time has 3 positive dimensions and 1 negative dimension, blah, blah, blah. I don't know all the physics behind it. What I want to say is that you can travel in either direction in space, but only one direction in time. And because the arrows were cutting across a spatial boundary originally, that's what led to a lot of problems. The arrow of time despite our inability to explain it, does exist, and leveraging that makes our lives a lot easier.
Very cool. Let's thank Jonathan. All right. We still have 2 exciting talks in this session. We have marathon sessions. Yes, so let me introduce Ryan Kavanagh from Université du Québec. Please take it away.
Hi, so my name is... Better? Yeah, so hi, my name is Ryan Kavanagh, and I'm very excited to be talking to you today about message observing sessions. And this is joint work with Brigitte Piętka. So communicating systems are ubiquitous. We find them everywhere from the Internet of Things, to the cloud, to the software that runs on our phones, and that powers the modern internet, like web and email servers. And by communicating system, I just mean a coherent system where the individual components interact with each other through communication. So for example, you can think about the interactions between your web browser and a web server. And communicating systems only work if all the components interact and communicate with each other according to protocols, which are sets of rules that say which messages can be sent and when. And miscommunication is very costly. So to take a particularly notorious example, a few years ago there was the Heartbleed vulnerability that was caused by a bad implementation of the TLS Heartbeat protocol in OpenSSL. And it affected all sorts of industrial entities, and it also caused the leak of 900 social insurance numbers from the Canada Revenue Agency. And to put this into perspective, it cost an estimated $500 million to address. Concurrent systems are notoriously difficult to debug, and so what we'd like to be able to do is we'd like to be able to statically guarantee that our programs communicate correctly. And if we're to ensure that our programs have the behaviors we want, we need to be able to precisely specify these behaviors. Fortunately, we already have some technologies that let us do so. In particular, session types let us encode communication protocols at the type level. And then a session type language statically guarantees that a program is going to communicate according to its protocols. And there are 2 main varieties of session types. So multi-party session types let us specify communicating systems top-down. So we can specify all sorts of interactions between collections of processes at a time, but the catch is multi-party session types typically aren't compositional. It's really a global approach where we must specify the entire system at once. In contrast, we have binary session types that let us specify systems bottom up. So they're compositional, they have all sorts of interesting varieties, but the catch is we can only specify local behaviors between pairs of processes. So it's a very local approach. And so this motivates an obvious research question. Can you have the best of both worlds? So I'd like to be able to specify global properties, as in multi-party session types, but still have some kind of compositional system, as in the binary session type world. And of course, I wouldn't ask this question if I couldn't answer it. So today we'll see how we can get compositionality and global properties in a binary session type setting. So let's kind of set the stage. What do I mean by a communicating system? Well, I mean a collection of processes that interact with each other through communication. So I'm going to treat a process as some kind of black box. And it's going to communicate over wires that are called channels. And communication on a channel must respect a protocol. That's to say, some set of rules that say which messages can be sent and when. And protocols can evolve over the course of a computation to allow for different kinds of messages. And so we're also going to assume a client-server architecture, where every process is going to be a server for some distinguished service. And it's going to be a client of some number of services. So here, graphically, I've put the server channel on the right, and the channels of which I'm a client on the left. And we can use a bit of syntax that I've put at the bottom of the slide to kind of summarize this graphical notation, where I'll put the channels that I'm a client of in square brackets, and I'll put the channel that I'm a server for in parentheses. And I use this C:(A) notation to mean the protocol for the channel C is A. So this is a session type here. And a recurring example throughout this talk that's going to really illustrate some of the key ideas is the bitstream protocol. So it's a recursive protocol that's going to say, I can send a bit 0 followed by a bitstream, so that's this B0:bits, or I can send you a bit 1 followed by a bitstream. And an example communication that satisfies bits is this bit 0 followed by bit 1, followed by a bit 0, and a bit 0, and so on and so forth. And we can deal with all sorts of more interesting protocols like queues and stacks and auctions, but bits are going to be sufficient to illustrate some of the key ideas. And a natural thing we might want to do is we might want to specify a process that flips bits. So let's consider this process F. Our specification is it's going to be a client of some channel I satisfying the bitstream protocol, and it's going to be a provider for a channel O satisfying the bitstream protocol. And what F is going to do is it's going to sit there listening on the channel I, and suppose a bit 0 comes along. Well, it'll take the 0 branch, it'll send a bit 1 out on O, and then it will recurse, and then it will sit there listening on I. And the problem is, the specification doesn't actually specify or enforce bit flipping, right? The identity process on bits also satisfies this specification. In fact, there are infinitely many processes that satisfy the specification on the slide. And the problem here is that traditional binary session types, they're too local. They don't give us a means of specifying relationships between communications on different channels. And so our contribution is a language called MOST that lets us compositionally specify communication protocols that depend on communications on other channels. And compositionality is important because we want to be able to specify programs bottom up. We want to reason modularly about our programs. We don't have to specify the entire system at once. And we want to be able to depend on communications that occur on other channels because we want to be able to specify things like input-output behaviors. And MOST has 3 key ingredients. So we introduce some novel syntax that lets us use type-level computation to specify these communication protocols. And then we give an interesting novel semantic framework for explaining what it means to have a protocol that has dependency, right? And then finally, we give a static type checking algorithm that says, given a specification, does my process, my program, actually satisfy that specification? So what does most syntax look like? Well, we have all of the binary session types that we know and love. So for example, we retain labeled choice. We saw an example of this with the bits protocol. So a labeled choice says, well, I can send you a label L, followed by a communication that satisfies A. Or I can send you a label R, followed by a communication that satisfies B. Right? So the bitstream protocol is this. We send you a bit 0, followed by a bitstream, or I send you a bit 1, followed by a bitstream. And now the novel part is we introduce this kind of big elimination, this type-level process that's going to observe some channel C, and then do something, give us a protocol based on what it observes on C. And so the operational intuition here is that this type is going to reduce to the type A if a label L is observed on C, and it'll reduce to B if a label R is observed on C. And we can have we have similar constructions for observing termination, for observing channel transmission, and so on and so forth. See the paper, the details are all there. So how can we use this to specify bit flipping? Well, if we remember our original bitstream protocol, we can define a bit flipping protocol that uses this big elim. So relative to some channel I of type bits, we're going to define a type called bits flip I. And it's going to be a case analysis on I, and it's going to say, if I observe a bit 0 on I, then I'll give you a unary choice where the only thing you can send is the bit 1, followed by something that satisfies the bits flip protocol. And if you happen to observe a bit 1 on I, then the protocol becomes this unary choice where the only thing you can send out is a bit 0, followed by communication that satisfies the bits flip protocol. And so now what we can do is we can revise our specification and change the type of O from being just bits to being this bits flip I protocol. And we can use this technique to specify any sort of stream, transducer, or multiplexer. In principle, you could use it to specify, for example, the results of DNS queries after doing a DNS zone transfer. You could use it to specify proxies and so on and so forth. And here I want to point out that the protocol, it really looks a whole lot like the implementation of the bit flipping process. That happens to be an accident. It's a really simple process, and a really simple protocol. You know, there's not a whole lot you can do there. But if you look in the paper, for example, we specify a fair auction where the specification and the implementation are really quite different. And so the first key insight is that we can specify these kinds of dependent protocols using a very restricted form of type-level computation, where we're going to lift a section of the process layer that does observation, that does message observation, up to the type level to kind of programmatically specify protocols. Now, one of the things we were after is a compositional system. So how can we reason about process compositions? So a natural thing we might want to do is we might want to chain two bit flipping processes together. So here I have a bit flipping process on the left. It's a client of a channel I, and it's going to be a server for some channel M that satisfies bits flip I. And let's suppose I want to feed that channel into a second bit flipping process. That's going to be a server for a channel O of type ID bits, where ID bits just says, well, I'm going to give you exactly the same thing that came in on I. And we can implement it in the same way as we implemented bits flip using this big elim. Well, if we want to reason compositionally, we'd like to be able to reason about the whole thing in terms of the specifications of the parts. So let's zoom in on the right process here, the right bit flipping process. Well, we notice that we've got this kind of issue here, where the specification depends on this channel that the process doesn't have access to. The specification of M and of O, mentions this ambient channel I that F doesn't have access to. And so what we need to do is we need to extend our specifications to track assumptions that we make about the ambient environment where we live. This helps ensure that the types remain well formed. Informally, what this means is the process has a given behavior provided the environment behaves according to the types in this ambient context that I've put in curly braces. You can also give it kind of a rely guarantee interpretation where you think, well, relying on the fact that the environment behaves according to the specification, I guarantee that my process will behave according to the types in my spec. So what does this all mean? I've given you some new syntax and some informal intuition. How can we make it precise? Well, we give our language a denotational semantics where the processes are going to denote sets of traces of messages, so things that can be sent back and forth. So if you consider the bit flipping process on M and O, well, it represents a set of traces. For example, the first trace says, if I receive a bit 0 on M, then the process will send a bit 1 on O, and so on and so forth. Dually, if it received a bit 1 on M, then it'll send out a bit 0 on O, and so on and so forth, right? So we have a different trace for every possible execution. And then what a specification denotes is also a set of traces that are allowed by the specification, and we need to account for these ambient assumptions. So we're going to add in these special elements that say we're going to rely on these behaviors in the environment. So for example, think back to the rightmost process in the composition. It had this ambient channel I, and it said I was a client of a channel M of type bits flip and a provider of O of type ID bits. Well, an example trace we could have is the trace we have here that says, assuming some bit 0 goes by on I, then the process is allowed to receive a bit 1 on M, and then allowed to send a bit 0 out on O. So it really just specifies which behaviors are allowed. So how do we type check? How do we statically ensure that our processes satisfy their specifications? Well, we give a recursive algorithm in the paper that recurses on the structure of the processes and the specifications. And what it does is, as it checks the process, it's going to generate a set of constraints on the environment. So some set of constraints T, it's going to be an output of the algorithm, of the typing judgment. And then when we come to a case where we need to type check a composition, well, from the recursive calls, we're going to get two sets of constraints, and we're only going to allow the composition if each process satisfies the constraints that the other imposes on it. So it's really a constraint generation and constraint checking algorithm. And our type checking algorithm satisfies a soundness property that basically says it's correct. So if a process type checks against its specification, then all of the traces that the process has are amongst those that are allowed by the spec. Remember that the spec gave you a set of allowed traces, so the type checking algorithm basically says if it type checks, all of the behaviors are amongst those allowed by the specification. So the algorithm is in some sense correct. Now, most is not the first dependent session type systems. There are others, for example, value dependent session types and label dependent session types by Peter Tiemann in the back. And these session type systems allow for dependencies on previous messages sent on the current channel. And the key difference with most is we allow for dependencies between different channels. So instead of saying we can only depend on what previously went forth on this given channel, we're going to allow you to relate communications on different channels. There are also, of course, multi-party session types, which allow you to specify these kinds of rich interactions, but again, the catch is it's really a top-down approach, it's not compositional. So most is really the basis for a whole lot of future work. So it's a linear type system. And so one of the things that would be nice to do is be able to introduce sharing so that we can specify and verify shared services, like, for example, databases or shared data structures. It would be nice to have a subtyping relation that lets us compose processes where the two types are not equal on the nose. At the moment, we require that if you compose things, they must have exactly the common type. This is a bit restrictive. We'd like to be able to relax this. Of course, it would be nice to have a compiler so we can do case studies, play around with this. And one of the things I'm interested in is how can we characterize this expressiveness gap between most and multi-party session types. Multi-party session types are more expressive than most. You know, we have more restrictions, but where exactly, how can we pinpoint where is that demarcating line? And so with that, I'd like to thank you for listening to the talk, and I'm happy to take any questions.
Okay.
Thanks. Very cool work and good talk. Thank you.
Thanks.
So in multi-party session types, a key thing is that the global types needs to be well formed.
Yes.
And everything depends on that, really.
Yes.
So what's the corresponding ingredient in your work?
The corresponding ingredient in our work? So we do have, we check well-formedness of types during the type checking algorithms. So you could give some kind of ill-formed spec. We don't, a priori have a well-formedness condition on types. Originally, in a prior version of this work, there was a judgment that said, is this type well-formed given some other context of types? That ended up being a bit superfluous. It just made the theory a bit more complicated. Now we basically say you can write some stuff down, and if it manages to pass through the type checking algorithm, you're okay. And semantically, this is perfectly fine because, if the semantics says your things are ill-defined, the type checking algorithm won't be able to check it anyways. Does that work out?
Well, thank you for the talk. That was very nice. I was wondering about the semantics that you presented.
Yes.
Is that a synchronous semantics?
Yes, it's synchronous.
So do you see any trouble in adjusting stuff for asynchronous semantics?
No, not at all. So I didn't mention it. So our traces have a notion of binding that I didn't get into that lets us easily model channel transmission. And basically, you could encode an asynchronous semantics using continuation channels. So basically, you add a new binding operator and you encode continuation channels that way so you can get asynchrony. So there's a section in the paper where we discuss how can you extend this to handle asynchronous communication. It's straightforward. The system used to be asynchronous, but just to make it clearer, we went for a synchronous version and paired it back.
Can I ask another one?
Sure.
Hi. Thanks, Ryan, for the talk. So I'm wondering about the experience of writing programs in most. So especially now that you have type-level computations and constraints on types,
yes.
Is type checking still decidable? Are there cases where you cannot have a type checker algorithm to work with your programs?
So it's all decidable. It's expensive. When we check composition, I haven't done the complexity analysis, but when you go to check composition, you need to check the constraints, and that's done with a predicate on sets of traces, and that just is exponential blow-up. So I sketched in the paper some ideas for how to make this more tame. There's some data structures you could consider that I mentioned, but there's no implementation as of yet. This is still future work.